Okay.
Morning, everyone.
Okay.
Evening if you're in Japan.
Sorry, I didn't hear what you said, Adrian.
I said good evening if you're in Japan or Australia.
Should I wait a minute for everyone to get in, or just?
Yeah, I would give it a minute.
Still taking.
Welcome, everyone.
Yeah, people are coming in. So Leah, the spotlight is just automatic from who's talking, or are you doling it out somehow?
Right now it's set on the speaker,
Okay.
and we can change that.
No. Okay, I'm gonna go ahead. I think. All right, so hi, my name is Maurice Smith, and I just want to sort of welcome everyone who's here, everyone, all the speakers, the audience members, the program committee members who helped out just tremendously in getting this conference going this year, and sort of welcome all of you to our meeting today, which will run from now to 10 a.m. Eastern time for approximately 3 hours until just about 1 p.m. Eastern time. And tomorrow it's starting. The time is offset an hour later, so it's going to be from 11 a.m. Eastern time in the United States to 2 p.m. I just wanted to thank everyone for the participation, especially the 40 plus faculty members who helped to score the abstracts and determine from the submitted abstracts the 10 that are going to be presented today and tomorrow. Just to sort of remind everyone, for this tradition of using sort of peer community to sort of decide what's going to be presented out of the submitted abstracts, and the program committee basically well, we're part of the scoring, and each sort of person on the program committee, the 40 plus people, score 4 to 5 abstracts, so that we can have so that each submitted abstract can have 5 to 7 scores, and we simply sort of average and normalize these scores, and then sort of select the top 10 abstracts for presentation at the meeting. The one caveat being that we have a limit of 1 abstract being presented per lab. Anyway, I don't want to sort of bore you with this process, but I just wanted to sort of make sure that everyone's sort of aware of how we go about things, I think, and just the importance of like the tremendous sort of participation we get from everyone in the community who helps out with this. So anyway, I'm personally really excited about the talks this year, both the sort of the 4 invited speakers who are going to sort of bookend each day, and the submitted abstracts, which I think are this year of really tremendous quality, top to bottom. And so I want to just start off by just introducing our first invited speaker, Tim Carroll, whose work I've just really tremendously admired over the years. There are just several sort of just I think really kind of just fantastic papers that I've read over and over from his group, and today he's going to be talking to us about, sorry, and today his title is the title of his talk is Subcortical Control of Human Reaching. I'll turn it over to Tim.
Thanks very much, Maurice. Can you see that okay? All good? All right, so obviously this is a really provocative title, and I'm not trying to convince you that the cerebral cortex isn't important in reaching, but I do want to show some observations that might help reconsider what it's doing. Okay, so all of the work that I'm going to talk about rests on observations from a very simple reaching task. So people look towards and point towards a central location, and then when a target appears, they have to reach in that direction as fast as they can, either to the left or to the right. During this, we record their movements with an accelerometer so we can detect the onset of their limb motion and the direction. But most importantly, we're recording their muscle activity, their EMG, from the horizontal flexors pectoralis major. And because we're mostly interested in this muscle, we preload it by just a pulley system to make sure that it can either increase or decrease its activity as a function of target direction. So if we do this task classically, what we normally see is if we do lots of trials and then we average the muscle activity, we see that the activity builds up prior to the average reaction time when we are reaching towards the left, and decreases prior to the reaction time reaching to the right. But we can get a lot more information about this if we actually plot every single trial as a raster. So here we're doing that, and we can show the amplitude of the EMG activity as a function of contrast. So with white colors being lots of activity, dark colors being not much activity. And if we order these trials as a function of the mechanical reaction time, so when the limb actually starts moving, we can see that the EMG precedes it and it's closely related. So if we actually plot the time at which, the first time at which the background muscle activity changes as we are leading into the reach, we see there's a broad distribution of muscle activity onset times that precedes but pretty well matches the manual or mechanical reaction time. However, we can do some funny things to make some different things happen. So this is a task developed by Rebecca Kozak and Brian Corneal's lab. And when we, oops, now I can't do this. I can show you what it looks like. It's very fast. You probably missed it. So I'll show you a different version slowed down. So this is 4 times slower. So you can see we have a ball which drops and then it disappears behind the barrier, suddenly appears, and then we reach to it as fast as possible. So when this happens, we get something slightly different happening. We get what we call an express response, which if we look around about this region, around 100 milliseconds after the target has been presented, we get this kind of line of muscle activity increasing here, which shows up in a blip in the average, and then a little decrease in activity in this case, which is time locked to the target presentation. And if we plot again the change in EMG from baseline as leading up to the reach, now we see a very tightly time locked band of EMG, time locked to the onset of the move of the target, either for increases or decreases in muscle activity. Now, it really does look like we have 2 separate types of control signal here, one of which is very early and very time locked to the target, but is not sufficient probably to initiate the actual mechanical reach. We're not obviously the first to show this. It's been known for quite some time. So Brian Corneal first showed it in neck muscles of monkeys in 2004, and Andrew Brzezinski and colleagues showed it in the limb muscles of humans in 2010. And it didn't take long for people to realize that this pattern of behavior seems to resemble what we see in saccadic eye movements. So for saccades, you can see 2 distinct bands of behavior. We call this first early mode, the express mode behavior, and the later, more spread out mode, the regular saccade behavior. Now, we know that for saccades, an area in the midbrain called the superior colliculus is crucial for developing the metrics of these things. And if we record from neurons in the superior colliculus, visuomotor neurons, what we see is a very reminiscent pattern to our muscle activity over here. We see a time-locked first burst, which is time-locked to the target onset, and then a later burst, which is time-locked to the onset of the saccade. So because of this and many other reasons, many people have speculated that what's actually happening here is that for this express component of our reach muscle activity, we have a very short pathway which goes relatively directly from the retina to the superior colliculus, or indirectly via the geniculostriate pathway to the reticular formation, where we conduct all the necessary computations necessary to produce muscle activity to move the limb to a visual target. Now, this obviously differs quite a lot from the traditional thinking of how we make visually guided reaches. So here we have a geniculostriate pathway to the parietal cortex, where we do lots of multisensory integration and coordinate frame transformations, then to the motor cortex, which has a direct connection with the spinal cord via the corticospinal tract. So this is the typical way that we would think about visually guided reaches. Despite the fact that it is well documented that there are multiple brainstem pathways that also get to the spinal interneurons and motor neurons that could potentially involved in controlling movement. It's also the case that people are starting to realize much more, and Paul Chizek's done this really well and comprehensively recently, that any new evolutions in brain function need to work with and evolve through the structures which phylogenetically preceded them. So the first earliest jawed vertebrates, 550 million years ago, had visually guided behavior mediated through the eye to the optic tectum, which is a version of the superior colliculus, to the reticulospinal tract to produce motor behavior. And if we look at some currently existing animals at different levels of complexity, we see that animals such as frogs, which can produce pretty impressive visually motor behavior, have a brain which actually quite closely resembles the midbrain and brainstem of the human. So this obviously begs the question, exactly how much can the midbrain and brainstem of the human system do? Is it capable of producing and controlling visually guided reaches? And if so, what's the cerebral cortex doing? So I'm going to address this problem from the perspective of these observed express reach responses, which I've talked about. So I think there's a few key questions we want to address. So I've shown you this in fairly contrived lab tasks so far. So there really is a question of, is this just a peculiarity of those tasks? Is it vestigial and not really important? Or is it actually a core feature of voluntary limb control? So to address this, I'll talk about lots of behavioral observations about the properties of this express reach activity. Another question is this express limb response really subcortical in humans? So we don't have direct evidence of this. So we've done some non-invasive brain simulation work to try and address this question. And obviously, we need to answer the big question. So what do all of these observations imply about the role of the midbrain and the brainstem in human sensory motor control more broadly? So all of the work from my lab that I'll talk about is at the basis of an Australian Research Council discovery project, which involves Guy Wallace, Amar Daruji, Jerry Loeb, and Brian Cornell. And all of the work's been done by some really hardworking and talented students, and Rechu Divakar, Samuel Contamori, and Young Sao. So, is the express activity vestigial, or is it a core feature? The first bit of evidence I'll give you is that this activity can actually be really large. So depending on the circumstances, you can see here's a very, very crisp and large time lock activity and inhibition. And if we look at the average plot over here, we can see that the express behavior is just as large as the later voluntary behavior. Now, some of this might be because of temporal alignment in averaging, but if you look at individual trials, we can see that very large EMG activity can precede movement onset and precede the second burst of EMG. Secondly, this express reach activity is actually closely associated with reaction time, or negatively associated as well. So in the cases where we have a lot of express reach activity, large magnitude in this time zone, then we get short reaction times, and vice versa. If we don't have much express reach activity, we get a longer reaction time. And this is held up over multiple subjects and conditions many times, this negative correlation. So this shows that the express behavior, the express activity is serving an important functional role of making our limbs move faster. And that may not be important in many of our lab tasks, but it's certainly important from an evolutionary perspective if fast movement was the difference between getting lunch or not. The next bit of evidence is that express limb activity actually can reflect the appropriate coordinate transformations to deal with discrepancies between eye and hand position. So we don't always go around looking at our finger. So Chao Gu from Brian Cornell's lab did a fantastic study to illustrate this. So they had 3 different setup conditions where either the eyes and the hand were aligned or they were misaligned, so that if the central target was presented, it was in eye-based coordinates rightwards and hand-based coordinates leftwards, or vice versa. And the crucial bit of evidence is here. So we can see normal short and latency express behavior for left and right targets. But the crucial bit is for the central targets. And in both cases, the central target express activity was coded in hand space rather than eye space. This is what's necessary if it's going to be functionally useful. We need to be able to transform wherever the target is in our visual field into appropriate direction of movement, depending on where our hand is. And this can all be done within 100 milliseconds. Another bit of evidence is that these express responses I've mentioned resemble closely the corrections we get to target jumps that occur while we're in the middle of reaching. So if we ask a person to reach straight to a target, and then we move the target halfway, which could happen if we're reaching to something that falls or someone bumps it, then we get these very, very fast corrections within 125 milliseconds for the actual mechanical response. And crucially, these corrections are always towards the physical direction of the perturbation, even if we ask people to reach in the opposite direction, so essentially an anti-reach task. This is clearly a really highly functional phenomenon. Okay, the next bit of evidence I'll talk about is these express responses are enhanced when we give people cognitive information to allow them to predict what's coming up. So here we have our standard dropping target, which will then reappear behind one of these barriers. But if instead instead of giving them an uninformative fixation cross, we give them a cue, which tells them with 75% validity which side the target's more likely to appear on, then we get much stronger express behavior for these when the target location is validly cued, compared to invalid cues or control situations. Now, if we look at this over a number of subjects, we see that the actual initiation time of our express response is enhanced by the valid cues. Also, express responses are influenced by the predictability and timing of targets. So if we know exactly when the target's going to appear, and so when we need to release our movement, we can have stronger express behavior. So here we have our standard dropping target, which we can predict about with very strong accuracy when the target will appear because we can extrapolate its motion. And here we have a situation where the target simply disappears and then reappears at some random time later. Again, we have stronger express behavior for the predictable timing targets than for the unpredictable timing targets. And this occurs over all subjects in terms of the initiation time or discrimination time of the express behavior, as well as the magnitude of that express behavior. So what's happening here? So this suggests to me that we can have a top-down spatial and temporal priming of the state of this subcortical system involving the superior colliculus and the reticular formation. So what we, and this results when we get our target appearing and our visual information hitting the colliculus in a larger and more likely express response. So this suggests to me that this express behavior is not an accident. It's something that the cortex in the brain and our strategic behavior is deliberately priming the subcortical system to get it ready to respond. Why would this occur if the superior colliculus and the reticular formation weren't required to produce control signals for reaching? The next bit of evidence I'll tell you about is that we actually get express responses to non-visual targets. So here we use some auditory targets, and this is work from Yang Sao. And if we represent an auditory target, make a click sound to one side or the other and ask people to reach to it, we can actually get express behavior to the auditory target. Now, it wasn't as common and it wasn't as prevalent across subjects, but here's one subject who shows a very strong express response to an auditory target, which is comparable to their express response to their visual target. And you can see here in the average that it's just as quick and early, even though the reaction time for the movement is actually slightly slower for audition. So we can get express responses to vision or to audition. If this system is going to be useful functionally, it needs to be able to integrate information from multiple senses and produce appropriate behavioral responses. So here we produce both vision and audition sounds at the same time. We made them either congruent to the same side or incongruent, so that we had to reach to one or the other of the two responses. So if we look at the situation when people reach into visual targets, if we had a congruent situation so that the vision and the audition were on the same side, we get an extremely strong and crisp express response. It's very early. Whereas if we have an incongruent situation where people are reaching to the visual target, but the click is on the other side, we have a weaker and delayed response. Similarly, if we ask people to reach to the sound target and ignore the vision, when those two things are congruent, we get a crisp and strong express response. But when they're incongruent, we lose the express response altogether. So again, if we look at the onset time of these express responses, we have a strong, congruence effect, both for the vision and for the sound across multiple subjects. So we tried to address the question of whether this express behavior is a vestigial peculiarity or a core feature of voluntary limb control. I've shown you that the express activity can be very large, that it results in earlier limb motion, which is important in real world situations, that the express pathway probably underlies corrections of ongoing movements to visual events that is highly functional, that we can have, when we increase the predictability of the targets, we increase the express response prevalence and magnitude, which suggests that it's not an accident, something we're intentionally doing, and that express responses can solve coordinate transformations for eye and hand misalignments, and they can respond appropriately to multisensory integration. So I hope you can agree it's very unlikely that these are a vestigial peculiarity. So the next thing we wanted to look at is, can we get some information about whether or not these express limb responses are actually subcortical in humans? So to address this, we use non-invasive brain stimulation. We use transcranial magnetic stimulation, which induces electrical fields inside the cortex, and is thought to predominantly activate these corticospinal output cells indirectly by activating axons of corticocortical neurons or intracortical interneurons. So the state of these corticospinal output cells, their excitability state, can influence the size of the descending volley we get to here, and also then the response of the muscle response we get via EMG. So if the express response is driven by the motor cortex, we should expect to see facilitation of those responses early on, just prior to the muscle activity we're seeing. So Rechu Divakar did this work, and we had our standard falling target paradigm, and we stimulated the brain after the target appeared at multiple times, or we sometimes stimulated the brain when we withheld the target, just to make sure that any responses we saw were actually target directed and not just due to anticipation of a target appearing. We also had a third control condition where we put the target on, but we didn't give TMS to make sure we could see what behavior was occurring in the absence of brain stimulation. So we stimulated 60, 70, 80, 90, and 100 milliseconds after the target was presented. And we asked people to reach either towards or away from the target, depending on in separate blocks. So here's some motor evoked potentials, the EMG responses we get from these brain stimulation from the pectoralis muscle while people are performing this task. So first of all, these are the responses we get when people were expecting to see the target, and we stimulated 80 milliseconds after when the target should have appeared, but there was actually no physical target there. So this is our control condition. And you can see that from the timescale here, these responses are very short latency, around 10 milliseconds long and quite brief. So it's likely they're mediated by the fast corticospinal tract. So if we measure the size of this control, and then we look at how these responses are modulated as a function of time for left and right targets. In this subject, we see a clear disinhibition of the excitability for right targets when the pectoralis major needs to relax in order to reach towards the target, and maybe a hint of excitation for the left targets. If we look at this across multiple subjects, so this is 20 subjects, and these are confidence intervals, we see a very clear dissociation in the brain responses, magnitude of the brain responses to left and right targets by 70 milliseconds after the target's been presented. And this grows larger over time. This is very early. Within 70 milliseconds of the target appearing, the corticospinal tract knows which direction the limb needs to move. Crucially, when we did the anti-reach task, we still saw this effect at 70 milliseconds, and it was still in the direction of the physical target. So these excitability changes are associated or appropriate to direct the hand towards the physical target, not towards the eventual reach direction. But by 100 milliseconds, we've already done the computations necessary to switch that so that we're now, excitability is now appropriate to bring the hand towards the target. Just for comparison's sake, the actual mechanical reaction times range between 170 and 300 milliseconds for the pro-reach and a bit longer for the anti-reach, only about 30 milliseconds difference. So you can see that these excitability changes vastly precede the manual response time. So what's causing this? So we have to remember this, it's tempting to think that this is clear evidence that the motor cortex is producing these responses. But we really need to consider the fact that the responses to this brain stimulation could be mediated in the cortex or at any point below the cortex as a function. Yeah. So if we need to look at what could be going on. So one thing we can tell here is what's happening in the motor neurons. So if the motor neurons are active prior to the movement, then we should see it in the EMG responses we get. So here we see an individual subject's EMG, and there's not much evidence of changes in EMG before the main burst of EMG some 150 milliseconds later. However, if we look across all subjects and we plot the muscle activity without any TMS in the same windows of measurement that we use for our TMS measurements, we do see some trends towards EMG changes which reflect the target position. This is also the case for the anti-reach, although less likely at these important latencies here. So we need to remember when even though we're stimulating the motor cortex, it's possible that our responses are modulated subcortically. And we've seen some evidence that maybe our responses to the brain stimulation could be mediated because of the motor neurons being active and therefore being more responsive. So we could have the same descending volley, but a larger response of the motor neurons. We could even have some indirect responses via interneurons within the spinal cord, which could be causing this. And if we think that the midbrain and reticular formation system is interacting here, it's possible that all of the effects that we're seeing with our brain stimulation could actually be mediated subcortically. So to get at this, we actually need to stimulate the brain in a different way, perhaps using transcranial electrical stimulation. And we've got current work that's, current work is ongoing to do this. So I'm not going to talk about today, but luckily Suzuki and colleagues have done a fantastic study which basically did the same type of work in a reaching task which had target jumps. And they used multiple converging bits of evidence to make the strong case that the modulation of the brain responses during this task when the target was jumped was in interneuronal circuits. So we've shown we've addressed the question of whether express limb responses are subcortical in humans. We don't have a definitive answer. We certainly need more data, but the results we have so far are consistent still with subcortical modulation of brain responses. They also show extremely rapid knowledge in the corticospinal tract of which direction that the target is going to be in, and also rapid transformations into a cognitively determined reach direction. So the final thing we need to think about then is what do these observations imply about the role of the midbrain and the brainstem in human sensory motor control? So let's consider some possibilities. So let's think about first, before the target is presented, what might be happening in various brain structures. So I suggest that there's bidirectional communication between our subcortical centers for the express reach behavior and the cortex by the thalamus, and also direct inputs from multiple cortical brain centers. And this is to set the neural state of these circuits appropriate to the context. So for example, setting up a situation so that it can perform appropriate coordinate frame transformations. Now, the preparatory state here should be maintained in motor cortex and the reticular formation, perhaps via basal ganglia interactions, to prevent a change in state to releasing movement. Once the target is actually presented, I think that what might be happening is that those cortico-basal ganglia interactions cause a shift towards output potent states, both in the motor cortex and the brainstem, illustrated here by a lighter blocking line, such that the first wave of visual target information actually now will cause an express response. And this is our early blip of EMG, the first blip of EMG that we see. And the reticular formation role here would be integrating sensory inputs with preparatory state information from all of these cortical areas to generate appropriate control signals to move the hand in the right direction. Now, the controversial part comes here is what's happening for the second part, the voluntary part of the EMG that's after the express behind. So at this point, it's probably what I suggest is happening is that we have corticobasal ganglia interactions, which now generate an overt state change to output potent state and a movement release signal. So here we have the basal ganglia interacting, for example, with the motor cortex. And at this point, we can have release of motor commands, which might be sending direct control signals to the spinal cord, perhaps bypassing the brainstem. But it's also possible, either together or instead of, that the basal ganglia also has a release signal to the midbrain and brainstem, and the reticular formation integrates information from the sensory inputs and the cortical inputs to produce control signals which go to the spinal cord. So I don't think we have the evidence yet to distinguish between those two possibilities, but my money is on the brainstem. Thank you very much for your attention. Really like to thank all of my collaborators in the funding group. I can't hear Maurice.
Oh, sorry. I was muted. Thanks, Tim. That was really stimulating. I have a quick question of my own, and that is, so you reminded us at the beginning that express saccades are possible at latencies of just 100 milliseconds or so. I think in the data you showed, 10-20% of saccades were express saccades, but you said that these sort of express EMG activity wasn't quite enough to initiate movement on its own. But then you showed a plot of the correlation between this express EMG activity and reaction time, and you showed reaction times down to, I think it was 140 milliseconds or so. Right. But I'm just wondering, but are those sort of extreme low reaction times at the sort of extreme left part of that plot? Were those actually like pretty much directly related to this directly coming from this express EMG activity? I mean, given that there's going to be some sort of transduction time between EMG and force generation and movement, I'm not sure what your threshold was for reaction time. So
yeah, I mean, it's a great point. So I guess, if the express behavior is large enough, it'll definitely produce an overt response. And I've certainly seen situations where the manual response is probably triggered by the express response. But you need to think about musculoskeletal mechanics. So with the catch-like properties of muscles, the first action potential, has to be a lot of muscle fibers to get an action potential at the same time, generate enough force to start moving the arm. So it's probably more likely that the second and third action potentials is when you start getting enough force to actually start moving the limb. But that doesn't mean that the first blip is not important. It's always going to be important, even if it's 100 milliseconds before the voluntary latency. It's still going to be, the calcium is still going to be there, still going to be actually ready to summate when the next bit of EMG arrives.
I think Adrian told me that he had a question. Adrian, do you still have a question?
I think we should hear the audience questions first before I.
Okay. All right. So Paul Gribble says, wonderful talk, Tim. Thank you. What do you think the functional role of this short latency response is for arm movements in humans?
Well, I think, it's an open question, right? There's a continuum between not important at all to important for every single arm movement. I think it's somewhere in the middle there. I think it's pretty important for whenever we try and make rapid movements, even in the cases where we don't see this expressed behavior or the expressed muscle activity. I think that the subcortical system is probably being primed and probably then transforming cortical and sensory inputs even for the secondary bursts that we see. So I think it's probably really important for a broad range of gross, fast limb movements.
Okay. John Krakauer asks, what do you think about the precision of these express responses compared to longer latency responses?
It's a good question. We haven't looked in detail at that. It's something that's a little bit hard to do because the precision is always going to be dominated by towards the end point of the movement, and so we haven't got a good way yet to separate the express component of the behavior from the longer latency component of the behavior. I suspect it's not going to be as precise, and in our tasks today, we're not really aiming for any type of precision. But we are doing things which, so Sam's got some work which he hasn't published yet, which is looking at, is this system tuned to the amount, the magnitude of the reach or the length of the reach? So do we get a larger response when we have to make a longer reach? And that seems to be the case. So I do think it's functionally tuned and it is appropriately target directed, but I would guess that it's probably not as precise as a longer latency, potentially cortically mediated component.
Reza Shadmir has a question. It's a little bit similar to mine. He says, for saccades, express saccades are, complete movement. Do you think there are circumstances where there could be sort of complete reaches that are born out of this express responses?
Yeah, I mean, I think so. I mean, you have to remember that saccades are limited by the omnipause system, and they've got, and the muscles, the eye themselves have extremely low inertia. Most of our limbs have pretty high inertia, so we need long-lasting, like sustained bursts of EMG to generate enough force to produce it. So it's possible that a single burst with probably a single action potential on any given motor unit isn't going to be sufficient to produce large EMG. Again, the question remains whether that secondary burst of EMG is actually a separate pathway via the cortex or actually works through the subcortical pathway and is integrated at the brainstem to produce the secondary bursts. And as I said, we don't have the evidence yet, but my mind is on the second option.
So one final question from Lee Miller, and he asks, the concept of a release signal seems in conflict with the null/potent model of Kaufman et al. Which is it that you have in mind? Well,
I guess I'm sitting on the fence there. I mean, I conceive of it of being there is somewhere that there's a. So the reason why probably this secondary burst is so broad is that there's some kind of cognitive or processing step that is involved in generating some decision to release. So whatever the mechanism for that is, whether it's a gate or whether it's a shift in state, I don't have the evidence to talk about. I probably lean towards the shift in state. That seems to be the best evidence at the moment. But I don't think it matters materially for my point.
Okay. All right. Well, thank you so much. I really appreciate the talk, and I think our audience did too.
Thanks. It was a pleasure.
Yeah, thanks, Tim. So there's a lot more good questions. Maybe you can address some of those in the Q&A area directly. So we're going to move on to the submitted talks. And our first talk is going to be from Yuto Makino from the University of Tokyo. Welcome, Yuto.
Thank you for your introduction. So please, I shared my screen. Yeah, so can you see my slide?
Yep, we can see.
Okay, start. It's a great honor to be able to speak to you today. So I'd like to talk about the presence of the mechanism to produce a feed-forward motor command based on the temporal transition of visual error. So let me begin by talking about the background of this study. So the motor system consistently makes errors during movement and has the ability to modify the motor command within a trial and in the subsequent trial. In a reaching task, for example, the visual motor rotation induces sensory prediction error. Then the motor system corrects the movement, trying to cancel the error within a trial, which is online correction by feedback response. And also, in the next trial, it corrects the movement in the opposite direction to the error, which is offline correction by motor learning. Especially the mechanism of offline correction plays an important role to achieve precise movements. One of the promising ideas for the production of motor command for offline correction is feedback error learning hypothesis, in which the motor command for online correction serves as a teaching signal for offline corrections. A recent study, Albert and Shadmir, examined the relationship between both corrections to force field perturbation. They proposed an idea supporting feedback error learning hypothesis that the motor command for offline correction was a fixed time shifted copy of online correction about 125 milliseconds earlier. However, several issues remain. First, some studies reported that the temporal patterns of online response are not preserved in the offline corrections. When the movement error was temporarily manipulated, for example, the location of the force pulse was modulated, the online correction varied with the temporal pattern of error. But such specific patterns are lost for the offline corrections. Second, even when only endpoint error was provided, which means online correction was absent, however, the offline correction still exists. So thus, it has not been fully elucidated how the MOTAC system can generate the MOTAC command for the offline correction. So this study tries to clarify the mechanism of generating the temporal pattern of the MOTAC command for the offline correction by using a more advanced experiment paradigm. So now I'll introduce the procedure of this study. So participants move a cursor with their unseen hand toward the front target 20 centimeters away. So they were instructed to move the hand to the target, not to use any explicit strategy. So in the perturbation trial, the visual cursor was laterally shifted. Then the online correction was generated in the opposite direction to the shift. These online corrections were obtained as a force against the force channel, so which constrains the movement trajectory from the start to the target. In the next probe trial, offline corrections were also obtained as a force against the force channel. So the cycle of the perturbation and probe and two washer trials were repeated. So this paradigm combining the cursor shift and force channel is ideal because temporal pattern visual perturbation can be arbitrarily manipulated. So the onset and the pattern of the visual perturbation can be manipulated. So the next, the motor command for the both corrections can be directly compared by the temporal profile of force using force channel without being affected by the change in kinematics. So 3 experiments were performed using this paradigm to elucidate how the motor command for the offline correction generated based on the temporal pattern of online corrections or visual error. Okay, this slide is about the data processing. To evaluate both corrections, we first measure the lateral force to visual perturbation, which has the temporal patterns symmetric about the targeted movement. And we regarded the temporal profile of corrections as the difference between the response to the left perturbation and the right perturbation. So through this process, we acquired the temporal pattern of both corrections. Moreover, we quantified the response size of both corrections as a lateral force integrated from onset to the offset. Now I'd like to move on to the experimental results. So experiment 1 was performed to examine whether the motor command for offline correction was a fixed time shifted copy of the online corrections. When the cursor was laterally shifted by 3 centimeters at 1 centimeter location, the online correction started 200 milliseconds after the cursor shift, like this. In contrast, the offline correction started before the movement onset. So when we manipulate the shift location from 1 cm to 7 centimeters, the onset of online correction shifted depending on the cursor shift location. So when we manipulate the shift location to 30 centimeters, the onset of online corrections shifted equally. So if the offline corrections were merely the online corrections shifted with a fixed time, the onset of offline corrections could be changed gradually depending on the shift location. However, the experimental result indicated that the offline corrections started equally before the movement onset. So in experiment 1, these perturbations were induced like this. So both corrections to these perturbations possessed the same characteristic as mentioned before. So to elucidate the relationship between both corrections, we compare the online and offline correction to the same perturbations. First, comparing the response size, which quantified both corrections, there was a significant correlation between the amount of online and offline corrections. So this result is consistent with feedback error learning hypothesis. Then, to evaluate time shift and similarity, we compute the cross correlation between the temporal pattern of online and offline corrections. The similarity was quantified as a max cross correlation coefficient, and the time shift was quantified as a lag between them. The figure shows that the similarity between both corrections. So there is a high correlation between them in all the perturbation, suggesting that the temporal patterns of online and offline corrections were reasonably similar. This result also was consistent with feedback error learning hypothesis. However, evaluating the time shift, the amount of time shift between the temporal pattern of online and offline corrections was not fixed. The time shift between both corrections was changed as the onset of perturbation was modulated. So rather, the offline correction equally started the movement onset. So I now summarize the experiment one. The first, the offline corrections were not the online corrections shifted with a fixed time. So the second, the similarity between online and offline correction would support the idea that the motor system uses online correction as a template for the offline corrections. However, there is a possibility that the similarity between online and offline correction were merely caused by the similarity of visual perturbation. So as the temporal pattern of visual perturbation in experiment one was stepped functions like so. So experiment two was designed to investigate how the drastic change in the temporal pattern of visual perturbation induced the online and offline corrections. So we prepared 3 shift patterns to impose different temporal pattern of visual error in experiment 2. The cursor was shifted by 3 centimeters at 1 centimeter location. Then in the first shift pattern, the cursor shift was maintained. The second was the cursor shift was removed at the second shift location, like this. The third was the cursor shift was reversed, like this. So also we manipulate the second shift location for pattern, like this. So the next figure illustrates the both correction in experiment 2 to these perturbations. So the upper part shows the online corrections and the bottom part shows the offline corrections. So for example, when the second shift location was 17 centimeters, the slight difference in the online corrections during the holding period induced a significant difference between the offline corrections. And surprisingly, the offline response size in the reversed condition dropped to near 0, though the online response size was large enough. Furthermore, focusing on the reversed condition at 5 centimeters, this is a blue line, so the biphasic pattern of the online corrections were entirely dissimilar from the temporal pattern of the offline corrections. So from these results, the first question is whether the temporal pattern of offline corrections preserved that of online corrections. We compare the similarity between the temporal pattern of both corrections. So let's take a look at the both corrections to the perturbation reversed at 5 centimeters. The gray line is the online correction, and the black line is the offline correction. So this data suggested that the online and offline corrections were not necessarily similar. So supporting this data, the next figure shows a cross correlation coefficient between both corrections to the all perturbation experiment 2. So especially in reversed shift conditions, the red square, there is a low cross correlation. So the manipulation of the second cursor shift reveals the dissociation between online and offline corrections. So the answer is a no. The temporal pattern of offline corrections does not preserve that of online corrections. So the next question is we next to clarify whether the motor system generates a non-specific offline corrections to visual error, we compare the temporal pattern of offline correction with each other's. First, we examine this question from a viewpoint of the response size. This figure illustrates the modulation of the offline response size with the manipulation of the second cursor shift. So the quantified offline corrections significantly changed not only by the shift pattern, but also the shift location. So indicating that these parameters of visual error induced a specific size of offline correction.
5 minutes left.
Next,
Okay,
we
five
compare
minutes.
the offline corrections in the perspective of similarity. This matrix shows the correlation coefficient between the combination of offline correction. There was a log correlation between the offline corrections induced by the different temporal pattern visual error. So the manipulation of the second cursor shift demonstrates the offline correction were specifically modulated with the cursor shift pattern. So according to these results, the motor system generates a specific offline correction to a visual error. So summary of experiment 2, the temporal pattern visual error has a significant impact on the temporal pattern, the size of the offline corrections. So however, what features in the visual error induce the specific temporal patterns of offline corrections? There are 3 possible factors inducing these strong effects. The first is the endpoint error. The second is the total error, the sum of experiment errors during the movement. The last is the transition itself, which is how the visual error is modulated. So the shift pattern in experiment 2 made all these factor changes. So we couldn't dissociate these factors in experiment 2. Experiment 3 was designed to clarify what features in the visual error induces a specific temporal pattern of offline corrections. So experiment 3.1 was performed to examine the effect of the temporal path transition of visual error on the offline corrections. First, we prepared 2 kinds of maintained perturbation. The 6 centimeter shifted or 3 centimeter shifted at 1 centimeter location. The temporal profiles of both corrections are modulated as well as in experiment 1. So this figure illustrates the relationship between the response size of online and offline. Moreover, we prepared 2 temporal patterns of visual perturbation, named increased and decreased perturbation. In increased perturbation, 3 centimeter cursor shift was repeated 2 times. And in decreased condition, the cursor was shifted by 6 centimeter and then returned to 3 centimeter. This perturbation and the other 2 has the identical error and identical endpoint error and different transition of visual error. Such manipulation did not influence the temporal pattern of online correction. However, but that significantly changed offline correction. So like this, comparing increased and maintained perturbation, there's a drastic change in offline corrections. So this difference of the transition had a significant impact on the offline response size, but there is no impact on the online response size. So similar results were obtained comparing the decreased and maintained conditions. So this result suggested that the temporal path transition pattern of visual error influenced not online corrections, but offline corrections. And the temporal transition, rather than endpoint error, contributed to shaping the temporal pattern of offline corrections. So experiment 3.2 was performed to examine the effect of the total visual error on the offline corrections. 4 types of perturbation were induced: sudden increase and gradual increase, and the sudden decrease and gradual decrease condition. Between sudden and gradual condition, while the endpoint error was identical, but the total error was different. For example, comparing to increased perturbation, so the offline response size to the gradual perturbation should be smaller because the total error was smaller than the sudden perturbation. However, the gradual perturbation induced a large size of online and offline corrections. So this figure illustrates that there is an inverse correlation between offline response size and total error. The inverse effect of the total error could be seen in the comparison between the decreased perturbation. So the continuous change, rather than the amount of error, might have a significant role to shape the offline corrections. this is consistent with the idea, the result in experiment 3, that the transition of a visual error had a large impact on offline corrections. So this is a conclusion. So first, the motor command for offline corrections are not a time-fixed version of that of online corrections. Second, the motor system has the ability to generate specific motor command for offline correction according to the temporal pattern of visual error information. The third, the temporal transition of visual error, rather the endpoint error and the total error, or the motor command for online correction, has an impact on modulation of the offline corrections. So this study indicates the presence of a complicated mechanism to generate the offline corrections. So applying machine learning algorithms might be useful to clarify the mechanism of transformation. So the important point is this study is the temporal transition of visual error has an impact on the offline corrections. Thank you very much. So thanks to my lab.
Thank you very much, Yuto. Very nice. So we have a few questions and we have about 5 minutes. So Reza Shadmer asks, and I think you maybe addressed this a little bit because he asked it kind of early on in the talk. Is it possible that the error response near the target is the key time point that is reflected in the offline correction?
Yes. Yeah, so I think this is important. So the error near the target is important. However, when the error near the target is the same, the transition itself is an important role to shape the offline correction. So the error information itself also is important, but the transition itself is also important. So both information has a role to the shape of the offline corrections. Yeah.
Okay, so Paul Gribble asks, he says, beautiful experiments, Yuto. My question has to do with how your results may be dependent on the task or task instructions. If the task were to track the shifted target over time, rather than simply to reach the endpoint, do you think the time varying form of the offline correction would more closely match the online correction? And if so, what would this mean?
Yeah, so yeah, so it's a good question. So, but the error itself we receive, so it's nonsense for me to movement. Yeah, this is a tough. Yeah, so I think so it's. I have to think about this so further. Yes. Okay, so please, yeah.
All right. Well, think about it. You can address this comment offline if there's a way you can answer them in the box. So I think maybe one more question from Alkis Joseph. He says, great talk instead of experiments. A way to look at this is that the offline corrections learn more from what happens towards the end of movement, probably because the task is to reach to the target. Could this be a case of feedback error learning where learning focuses on the part of the feedback correction as one gets closer to the target? So kind of a weighted, like FEL weighted towards the end of the movement.
Yeah, so we instruct the subjects to ignore the cursor, so the subjects don't try to get to the cursor near the target. So only they do the hand to the target. Yeah, but also the holding times the target, so they try to exert force is important information for I think the offline correction or online corrections. So it's important to investigate this force later.
Okay, and very quickly, Abigail Person asks, if you looked at offline corrections after a repeated perturbation rather than trial over trial, do you think a temporary locked correction would emerge?
Yeah, so what is
if you repeat the same perturbation for multiple trials, would you
Yeah, yeah.
start seeing a more clearly defined, more temporally defined response?
Yeah, so no, the perturbation was randomly so induced imposed, so that we cannot expect the temporal information of visual error. So only try to reaching, so then modify this explicitly. Okay.
Okay. All right. So thank you very much again, you two.
Thank you.
So let's move on to our next speaker, who is Tian Wang from Berkeley.
So could you see my screen?
Yes.
Cool.
All right. Welcome, Tian.
Thank you, Adrian. So hi, everyone. I'm Tian, and I'm a second-year graduate student from Rich Array Lab at UC Berkeley. And my talk today is about why is online feedback more effective than endpoint feedback for sensory motor adaptation. Okay. So in real life movement, we can receive different kinds of visual feedback based on the nature of the task. So for example, when we are making a reaching movement to an object with our hands, we can see both our movement trajectory when we are approaching to the object, and we can also see the movement consequence. This kind of feedback is considered as online feedback, that we are informed with both the movement trajectory and the consequence. However, we can consider another kind of situation. For example, imagine you are shooting a target with a gun. So after you press the trigger, you will immediately know whether you hit the center of the target or you miss it. So for this kind of feedback is considered as endpoint feedback. So we can only know the consequence of the movement, but we cannot see the trajectory. So here we come up with a question that how those two different kinds of feedback influence motor adaptation. So how we started this question in the lab, we use visual motor rotation task. But one potential problem with the classic visual motor rotation task is that the learning is contaminated with both explicit re-aiming and implicit adaptation. That is, there's a big gap between the late learning and the after effect we measured in the washout. So recently, we came up with the arrow clamp paradigm to isolate the implicit adaptation from the explicit re-aiming. So in the arrow clamp, the cursor will move to a predetermined direction, which is not relevant to the actual movement direction of the hand. Participants are fully informed that the cursor will not follow their movement, so they should ignore the feedback as fast as they can go directly towards the target. However, participants will still show the signature of implicit adaptation in the arrow clamp paradigm, that their hand will go to the opposite direction of the cursor during the training process. So we believe arrow clamp provides us with a cleaner way to measure implicit adaptation than the alternative method. So you can say that there's no difference between the late learning and the beginning in the washout phase. Here we started with revisiting a classic question that how the motor adaptation looks differently with online and endpoint feedback with our clamp method. So in the upper panel here, we show the relationship between time and the cursor distance. So in the online feedback, the feedback move along with the hand and is visible during the whole movement. While for the endpoint feedback, the feedback is only visible after the hand reached the target distance, and this only presented at the target distance. However, one thing we need to mention here is that because of the COVID and because our thousands of miles away from the lab last year, most of our data are collected with our web-based platform. So participants finish the experiment with the online, with their personal computer, and they make movement on the trackpad. So given that there might be some delay from our web-based system, and it could come from both the detection of the movement and the presentation delay. We will address this problem later, but here we just need to keep in mind that the endpoint and online feedback are not perfectly matched with the real movement. So here's the result. First of all, we can replicate the classic finding that online feedback induces larger adaptation than the endpoint feedback. So both the early learning rate and asymptote are larger in the online group. This is a quite intuitive result, but there's actually several differences between online and endpoint feedback. The most obvious difference is that the online feedback provides more information than the endpoint feedback. So first, the online feedback is presented at multiple positions, but endpoint feedback is only presented one position. And the duration of the online feedback is much longer than the endpoint feedback. However, there's another very important difference between online and endpoint feedback. That is, the on-site time of the online feedback is much earlier than the endpoint feedback. So this raises a question that what is the most important feature for the vero feedback to induce adaptation, whether it is the amount of the information or it is when feedback is available. So to test whether when feedback is available influence the adaptation, we ask that what will happen if endpoint feedback is presented earlier. To test this, we came up with a new condition called advanced endpoint feedback. So in advanced feedback, the feedback is presented at target distance right after the movement is detected. So the feedback is only visible for 17 milliseconds and remain invisible during a large proportion of the movement. The advanced feedback is only provided at one position and is as short as the endpoint feedback, but its on-site time is as early as the online feedback. So here's the result. Surprisingly, the advanced feedback induced a much larger adaptation than the endpoint feedback, and it reached the same asymptote as the online feedback. So it seems like presenting endpoint feedback as early as when the online feedback is available can fully compensate for the difference between online and endpoint feedback. We confirm that there's no online correction in all three conditions by analysis the movement trajectory. So then we ask, is the advantage in the advanced feedback, and this is special with our clamp paradigm. So we then try to replicate the difference between advanced and endpoint feedback with the non-clamp classic rotation task. So in both advanced and endpoint condition, the position of the feedback is determined by the heading angle. So the feedback position is determined at exact the same time for both conditions, but for advanced feedback is presented as soon as the heading angle can be detected, but the endpoint feedback will be held until the hand reach the target distance. We use a 35-degree contingent rotation, and here's the result, that in the late learning, both advanced and endpoint feedback group can compensate most proportion of the rotation, and we look into the after effect to see the implicit adaptation. So it is clear here that the advanced feedback induces a larger implicit adaptation than the endpoint feedback. So this means that the advantage of advanced feedback is nothing special with our clamp paradigm. So far, we already showed that the feedback on-site time seems to be an important feature that influences adaptation. As for control, we then further checked whether the manipulating amount of information provided by the feedback will also influence adaptation. We first extended the presentation time of advanced and endpoint feedback to match the same presentation time as the online feedback. So they are on average 100 milliseconds. So for example, for the advanced extended condition, the feedback appears at the target distance when the movement detected, and it will stay there until the movement ends. And for the endpoint extend condition, we present the feedback at the endpoint position for around 100 milliseconds. So however, for both conditions, they actually do not increase adaptation, which means that the duration of the feedback doesn't seem to be important for adaptation. Then we check the multiple position hypothesis by adding spatial continuity to the advanced feedback. In the advanced online feedback, the feedback is presented at target distance when the movement is detected. And during the movement, the feedback will reach beyond the target distance. Similar to advanced feedback, there's a gain in the advanced online feedback compared to the online feedback. So here's the results that the advanced online feedback doesn't increase adaptation compared with the advanced feedback. And to do with the potential ceiling effect with 15-degree clamp, we replicate advanced online feedback with a 2-degree clamp, and there's also no difference among 3 conditions. So that means the multiple position also doesn't seem to be important for learning. Here is the interim summary. So the amount of information provided by the feedback doesn't seem to influence adaptation, while the feedback on-site time seems to be the key feature that influences learning. So for the next step, we further check how the feedback on-site time influences learning. So previously, we only presented advanced feedback right after the movement is detected. So here we present a feedback at different time points after movement is detected. And since the average movement time is around 85 milliseconds, so the last three conditions are presented after the hand reached the target distance. So here's the result. We can see that when the feedback on-site time become early and early, the amplitude of adaptation become larger and larger. So here we see a very beautiful result that we have a monotonic function between feedback on-site time and the amplitude of implicit adaptation. However, as we mentioned before, since there's a delay in our system, so the advanced feedback actually doesn't mean the feedback is presented right after the movement on-site. The real relationship between cursor and movement should look like this. So there's a delay in between. So in an extreme case, if the delay is pretty large, then the advanced feedback may actually present it when hand reach the target distance. So it perhaps be the real endpoint feedback. Because participants finish the experiment with their personal computer and they're not using the same device, so actually it's not very easy for us to determine that what is the delay here. So to the best as what we can tell, in all the devices we tested in the lab, that the advanced feedback is presented within the first half of the movement. So anyway, to get rid of the concern of systematic delay, we bring this experiment back to the lab. And to measure the whole function of how learning changed with the feedback on-site time, we use a trial-by-trial design where both error direction and feedback on-site time vary across the trial. So the feedback on-site time is randomly sampled from a uniform distribution, vary from 200 milliseconds before the movement on-site until 300 milliseconds after the movement on-site. So it's cover both movement preparation, movement execution, and the period after the movement. And to make the time point we recorded as precise as possible, we measure the real feedback on-site time from the monitor and realign the movement on-site time with the real feedback on-site time during analysis. So we believe we can get rid of most of the systematic delay with our trial-by-trial design. So here's the result. X-axis is time, and we set 0 as the time that hand reached the target distance. So a negative value means that the feedback is presented before movement end, and positive value means after movement end. And y-axis delta hand angle, which represents the learning of a single trial. Start is the thank you. Start is the average time of movement on-site, and end is the movement end. So it is clear that for the error sensitivity function, it peaked at the middle of the movement. We then fit this error sensitivity function with a scale Gaussian for individual participants. And this is a result that at a group level, the peak is up at 120 milliseconds before the movement ends, and the average movement time is around 240 milliseconds. So the peak is right at the center of the movement. We then compute a corresponding hand position when the error sensitivity reaches peak. So on average, the hand distance is around 35% of the movement when the sensitivity reached the peak. So in sum, this figure shows the relationship between the movement time and the hand distance. So to sum up, the error sensitivity peak at half of the movement time when around 1/3 of movement has been finished. So finally, we asked whether feedback presented before the movement can also induce adaptation. So we replot the previous function with 0 point as the movement on-site. So a negative value means the feedback is presented before the movement on-site. And we focus on the period right before movement on-site. So here each bar is a bin of 40 milliseconds. So it is clear that the feedback presented before the movement can also induce a considerable adaptation. So here you can see that feedback presented up to 100 milliseconds before the movement on-site can still induce adaptation. So here's a conclusion. We show that motor adaptation is very sensitive to when the feedback is provided. And interestingly, the feedback is not most efficient when it is temporally aligned with the movement while the best time point to present endpoint feedback is in advance of the movement end. Moreover, we show that the advantage of online feedback to endpoint feedback doesn't seem to lie in the amount of information, while it perhaps that why the online feedback is better than endpoint feedback is because online feedback is available during the best time point to provide the feedback. Our results suggest an interesting question that why the optimal period to present the feedback is in the middle of the movement. So previous studies show that motor learning can be performed by directly comparing the inference copy of the motor command with the clamp feedback. So there will be a talk on it perhaps after half an hour. And so we think that our results actually, the error sensitivity function we measure actually reflect the accessibility of the memory strength of the inference copy to the cerebellum. So the optimal period in the middle of the movement may reflect two things. First, involuntary movement. The movement can be initiated before the plan has been finished. So the peak may reflect the time that when the motor plan is actually completed. So the second hypothesis is like there's a transmission time of the inference copy from the premotor cortex to the cerebellum. So the interval between the start of the movement and the peak may reflect the transmission time of the inference copy from the cortical region to the cerebellum. Finally, I want to thank everyone in the Coquiac lab for the helpful discussion. And thank you for your listening, and questions are welcome.
Thanks very much, Tian. So I have a question from Katinka van der Kooi, who says, beautiful results. To what extent do you think the results could be explained by motivation? Participants might be more motivated when only seeing small deviations early during the reach than when seeing a large deviation at the end of the movement.
Okay, that is a good question. I actually never consider about the motivation because it is a clamp feedback. So participants actually do not have any, won't use any explicit strategy. So I don't think they will explicitly compensate for the error. So I really do not think that motivation will be an important factor that influence learning.
Okay. Paul Greville asks, if the movement duration were manipulated, would the peak of the sensitivity function shift as well, or would it stay at about 150 milliseconds?
Okay, that is a good question, but yeah, because we didn't manipulate the movement duration, so we do not know the exact answer of that question. But I will, if you ask me to have a guess, I think it will still perhaps be 100 milliseconds after the movement starts, something like that. But I know the exact answer of that question. To the best I can tell, I think it will still in advance of the movement, and I think that is something we know.
Okay. Lawrence Snyder asks, does the error information provided prior to the start of the movement reflect performance on previous trials? If so, how is this conceptually different from late feedback?
Okay, that is an interesting question. So what we think about this result is like, so it's quite relative, very relative to a talk that you will say after two presentation. But what we think about this is like after actually, so participant will form the motor plan before they initiate the movement. So before we can detect the movements on site, there actually will be some EMG, something in your arm muscle, something like that. So we think it's still a correction to the current trial, but not the previous trial. So otherwise, we won't stay this curve go back to zero. It might stay at some positive value there.
Yue Du asks, would participants consider the advanced endpoint feedback as the feedback for their hand location at that particular time, rather than the feedback of the movement end?
Right, but if participants think of that, they will directly stop their movement after they see the feedback. So then they cannot finish the movement. They cannot reach to the target distance. Yeah. So we still think we do not know what participants exactly think about that, because we ask participants to ignore the feedback, ignore everything else they see other than the target. So we do not know what participants think of that exactly, but I don't think they will think that they reached the target distance at that time point. Otherwise, they will stop the movement in advance.
I think we can squeeze in one more question, maybe. Jean-Jacques Orban Desivry asks, what about the delay between error perception and the processing of that error, which is about 150 milliseconds for visual signals? Could that delay also influence the actual best time to provide feedback?
Yeah, that is a very good question. And we can see that it's that explanation offers a potential explanation to the result. That's the duration between the peak and end may reflect the time of visual processing that you see the feedback and you need some time to transfer this information to the cerebellum. Yeah, I can see that is a potential explanation of the result. Yeah. Okay,
and I think maybe we can do one more quick question. Chris Mile asks, could delay in the visual system also contribute? I guess that's very similar to the question. Yeah. So let's go with Hyosub Kim's question. Great work, Tian. Since you've manipulated timing and amount of information, have you also thought about manipulating the location of the clamped cursor feedback along its trajectory? The cursor shows up 1/3, 2/3, etc. of the way to the target distance.
Yeah, that's a good question. We actually did that. It's like we present a short online feedback where the feedback is only presented at the two first sample during the movement. So here's the result. So actually the radial distance will influence the learning, have a strong influence on the learning. That's the short online feedback will attenuate the adaptation a lot. So that is the reason why we keep all the feedback at the endpoint position, because we want to keep the size of the arrow the same across all the conditions. But the radial distance will actually influence the learning.
Okay. Thanks very much, Tian. I think we'll move on to the next talk now.
Thank you.
Thank you. So the next speaker is going to be Atsushi Yokoi from Osaka University. Welcome, Atsushi.
Okay, so how everyone? So can you see my screen and hear my voice?
Yep.
Okay, so today I'd like to talk about some link between pupil-linked arousal and error sensitivity. So imagine you are playing the drums, and what factor affect your motor learning and motor control? So obviously, so there's a reward. So and tons of studies also done in the motor control field. But there's also other factors that we know that should affect our motor control and learning. So which is, for example, arousal or surprise, sometimes uncertainty. And also there is some emotional stress like fear and anxiety. And also sometimes there may be some pain, maybe preclude your learning or motor control, and other some affective event and so on. So how can we deal with these many different factors? So one key component that might be affect these processes may be the noradrenaline, so which is a neurotransmitter originating from the locus coeruleus, which is a tiny nucleus in the brainstem, but it also sends very widespread in projection throughout the brain and subcortex, and also it's receiving the very diverse converging input from various brain areas, and that makes this noradrenaline. So here, so I call it NA for simplicity. So it's involved in a number of cognitive processes which I mentioned earlier, so including these ones. And actually, the NA is known to have a profound effect on the memory processes, especially it's related to some emotional events, so both acquisition and consolidations. And more importantly, the widespread projection from the LC locus coeruleus includes cerebellum and motor cortices, so which is critical structures for the air-based motor learning. Surprisingly, so little or no amount of study actually consider these relationships. So my ultimate question of this study is to ask to understand how NA affect motor control and learning, especially in humans. But to study the NA in humans, it's very difficult. So we can't do any invasive recording from the locus coeruleus, and also even for the fMRI. So locus coeruleus is very tiny, and it's still not impossible, but very challenging to image this structure. So the one way to conveniently and non-invasively assess this NA activity in human is to look at pupil diameter under the constant illuminations. And there have been many studies showing the beautiful correlation between the, for example, LC neuronal activity and pupil diameter. And also more recently, there's a solid stimulation study, so which basically says stimulation of the LC neurons reliably elicit pupil dilation. So using this pupil diameter, so I have been studying the relationship between the pupil-linked arousal / NA and the reach adaptation process in humans. And here is how typical task goes. And there's a center, hold, and waiting period. And importantly, to ensure the good quality of the pupil measurement, so we ask our participant always fixate on the target. So they're not allowed to look around whatever happens during the movement. And after some variable delay, so the target changes color and they're instructed to initiate the reach. But here again, so to ensure the good measurements, so we use isoluminant colors for this background and target and all the colors basically. And also we didn't provide online visual cursor feedback. And endpoint feedback is provided after the movement end. And basically, so the paradigm is like this. And also we instructed our subject to aim straight to the center of the target. And using this paradigm, so here in this study, I look at the single trial adaptation with various error sizes to see the relationship between the error sensitivity and pupil-linked arousal / NA. So which is basically consisting of 3 successive trials embedded in the a number of randomly chosen null trials. So there's 2 channel trials immediately before and after the perturbation trials. So for perturbation, so we applied trajectory clamp, which is simply just tilted channel trials towards clockwise or counterclockwise directions, ranging from minus 45 degrees to the plus 45 degrees. And a single trial adaptation, so we also didn't provide endpoint feedback during these perturbation trials. So all the error they receive is a proprioceptive error during the movement. And single trial adaptation is just quantified by comparing the force applied to this channel wall between channel 2 and channel 1 trials, so which is shown here. And you can see nicely the direction and the amplitude of this after effect is modulated by the perturbation size. And we quantify the single trial adaptation by taking the integral of the force value within the 200 millisecond windows just prior to the peak velocity. And it looks like this. And on y-axis you have that single trial adaptation measure. And also on x-axis, you have the proprioceptive error, which is calculated similarly, but during the perturbation trials. And you can see clearly that saturation of the single trial adaptation in large errors, large proprioceptive errors. and which is a nice replication of the previous studies. And error sensitivity is also clearly decreasing by the size of the error or perturbation. So we confirm that we see the reduction of error sensitivity in this paradigm as well. So next, let me show you how the PP react to these various sizes of perturbation. Here, so this is, I show you the a typical PP diameter change for the baseline period and the movement period, each aligned to the timing of the goal queue and the timing of the movement onset. So just around the perturbation trials. For the non-perturbation trials, so you see the typical decrease and increase of the PP diameter. So this is very robust phenomenon for the, this type of reaching task. And when we applied perturbation, so in this case, the perturbation is 45 degrees. So you see the very sharp increase of the PP diameter during the movement. And on the next trial, you get a slightly increased baseline PP diameter, but your PP duration is returned to almost normal. And after that trial, still we have some slightly increased baseline PP diameter. So by averaging the PP diameter during this baseline period, so here I show you the trial by trial change in the baseline PP diameter. So just around the perturbation event. And you can see clear modulation of the baseline PP diameter according to the perturbation size. And similarly for the PP duration during the movement, so to dissociate the baseline and the PP duration during the movement, we took the time derivative of the PP diameter, which is known to reflect the phasic noradrenergic activity, which again gives you some time course shown here. On y-axis, you have now the PP duration velocity, and on black, you have the PP response for the null trials, and on red, you have the PP response to the 45 degrees perturbation trials. And the difference between these two time courses is already significant before 300 milliseconds after reach onset. So again, we define some time window which mostly reflect this perturbation effect, like here, and then plot the trilateral change around the perturbation event. And again, we can see clear modulation, like here. So if we compare the online PP duration velocity between these two channel 1 and perturbation trials, so you get nice modulation of the online during movement PP duration according to the size of the movement error. Slightly non-linearly though. And also you have some nice modulation of the baseline PP change. So now in turn, this is a comparison between channel 2 and perturbation trials. So this is happening after the perturbation is experienced. So sometimes each of them is referred to surprise or some environmental uncertainty, and it looks that interpretation is consistent. So to summarize the experiment 1, so we replicated the decline error sensitivity at large errors, and also we added that the PP responses, both phasic dilation and baseline change, somehow scaled non-linearly with error size. And correlation between those two are also significant. So this is, here is a correlation between the baseline PP change and the error sensitivity, and this is PP dilation velocity during movement to the error sensitivity. So both are clearly negative relationship. So this is saying if your PP response is getting larger and larger, so your error sensitivity gets smaller, presumably through the error-induced any activity. But of course, this is just looking at correlation, and we need to clarify the causal relationship between them. So in the next experiments, we manipulated the PP-linked arousal state by applying some arousal manipulation stuff in the pre-movement period. So which should be task unrelated in perturbation trials. For manipulation, so we chose the auditory stimuli, which is called IAS2, so International Affective Digitized Sounds, so which is basically emotional sounds. So the reason we chose this auditory stimuli is auditory stimuli doesn't interfere with the pupil measurement, and also there's a non-reciprocal connection between locus coeruleus and amygdala. So this sort of emotional sound should affect NL activity through this pathway. And also there is these 167 sound clips are pre-rated in terms of either arousal or variance and so on. And here is arousal scores. The sound clips sorted by the arousal scores, and we chose the sounds from these both ends of the stimulus. For instance, for these arousing sounds, so you may see some female screaming sounds, or for this not so much arousing sound, you may see the sound of someone is yawning or something like that. And we actually confirm, so this rating is reflected in our pupil measurement. So here is a baseline period of the pupil dilation. After, so on x-axis, you have the time since the sound onset. So you have nice modulation according to the, this arousal rating. And also we confirmed that through the pilot study, so the effect of this baseline pupil change is maintained for another few seconds after the stimulus termination. So which is would be sufficient to cover the movement period and feedback period. So it should have some effect in the where the learning is happening. So using this arousal manipulations, we again tested the single trial adaptation paradigms. The first in this set of participants using the velocity-dependent force field. And later, so we tried to replicate the results by another set of participants with slightly different settings using the trajectory clamp perturbations. So the basic response of these perturbations is similar in both groups, and there's no significant difference between average amount of single trial adaptation. So here is a result of the manipulation effect. So for the first group, so manipulation, so please look here. So manipulation decrease the single trial adaptation. So which is consistent, somehow consistent with the result of experiment 1. So if you increase the arousal, baseline arousal, so you get the smaller error sensitivity to the same amount of perturbation. But however, in that something surprising happens. So when I opened up the result of the second group, so they showed a totally different tendency. Although there was not, the effect is not very strong, but direction is opposite. So in the second group, so the manipulation of the arousal somehow increased their error sensitivity. And initially I'm kind of surprised, and probably my pupil was dilating. But if you, there's a good way of explaining both results if you closely look at the baseline arousal state of each participant. So which is something famous inverted U effect of arousal and performance. So which basically says that there is an optimal point of arousal. So on that point, you get maximum performance, and on both sides of arousal. So if your arousal is lower than optimal point, your performance measure goes down. And if you also has a higher arousal state, so your performance also goes down. So in this case, so you get totally different direction of manipulation effect depending on where you are at this arousal state. So if you in the blue state, So increasing your arousal will increase your error sensitivity. But if you're already in this red zone, so increasing your arousal is just decreasing your error sensitivity. So we analyze our data by taking the mean arousal of each participant into account, so which is overall average of baseline pupil diameter, of course, excluding the manipulation effect. And here, so you see the overall average of the single trial adaptation. And somehow this shows some hint of inverted shape, but of course this is too noisy and this won't survive in a statistical test. And what we are not really interested here is the manipulation effect. So we calculated the manipulation effect by first z-scoring the adaptation within each individual and regressing error sizes out, so that there should be small fluctuation of error sizes around some fixed amount of population. And to the remaining residuals, we compare and calculated delta adaptation, which is a manipulation effect. For experiment 2A, the comparison is high condition and null condition. For experiment 2B, the comparison is high and low condition. And here you see the result. Again, on x-axis, you see the mean arousal participant. On y-axis, you see the manipulation effect. And each dot represents individual data, and this vertical line indicates median of these arousal. And color map indicates density of these data points estimated by the kernel 2D kernel density estimation. And this nicely reflects indicate the pattern characteristics inverted U relationship between the error sensitivity and arousal. So you tend to have more participants with positive effect on this lower side of the arousal, and you get more participants having the negative effect on error size on this right side of the arousal. And actually, so this mean arousal score is higher in the experiment 2A, which is consistent with they have the negative arousal manipulation effect. And for the experiment 2B, they have smaller and widely distributing based on arousal, which also consistent with their result. So
the time is actually almost up. Well, we're almost up to time for questions also.
Okay, so let me summarize. And so we observed these two results, so negative correlation between error sensitivity and pupil-linked arousal and the manipulation inverted U effect. And allow me to make some wild speculation that excess amount of pupil-linked arousal, which is presumably error-related and response, is actually decreasing error sensitivity. And there is some reason to think about this. So like here, and one is, so you get the smaller probability of complex spike for the larger errors. And activation of the alpha-2 adrenergic receptor in the cerebellum is actually reduced the releasing probability of the complex spike. And application of the alpha-2 agonist actually impair the LTD induction between the parallel fiber and the Purkinje synapse. And there are some studies suggesting the contribution of alpha-2 receptor is higher at the high NA concentration, and beta receptor is higher at low NA concentrations. And also some elimination of the NA terminal in cerebellum, or also the blockade of the beta adrenergic receptor slows your cerebral dependent running. So like this. So this, yes. So this is just a speculation, and obviously I need more data to test this hypothesis. But this is the end of my talk, and I'd like to thank these persons. And here's some trivia about pupil. Thank you. Sorry, and
thanks. I'm sorry, I got so absorbed by your talk, I forgot to give you the 5-minute warning. So we're really almost out of time, but maybe we can do one quick question. So Kunlin Wei asks, is the pupil response as a function of error size possibly caused by the eye movement itself? We know that eye movements can lead to pupil size changes.
So in the analysis, so I just removed all the trials which we detected the eye movement happening during the movement.
Okay. Okay, that answers that. So then he also asked, the average baseline pupil size is taken as the mean arousal for each participant. However, the pupil size has large individual differences. Can we make this equivalence?
Yeah, that's the important point, and thank you for asking. And actually, we normalized the pupil diameter within each individual using the amplitude of the light reflex. So I hope this makes the comparison meaningful.
Okay. Thank you, Atsushi. So I think we'll leave it there for questions. Let's take a break now for 10 minutes, and we'll resume at 11:55.
Okay, thank you very much.
Thanks to all the speakers so far, and yeah, see you in 10 minutes.
All right, everyone, welcome back. So we're going to get started with the second part of our program today. And so our first speaker of the day of this session is Olivia Kim. The title of her talk is Sensory Prediction Errors Are Sufficient for Implicit Adaptation of Withheld Movements. Olivia?
Hi, everybody. Thank you for that introduction. So my name is Olivia, and I'm a postdoc in Jordan Taylor's lab. But today I'm going to present to you some work that I've done in collaboration with Alex Florence and Sam McDougall at Yale. But before I start unpacking this title, I want to take a moment to step back and consider the potential influences of imagined movements that are not performed. So conventionally, we consider that there may be a role for mental imagery in improving motor performance. So for instance, suppose that you're a baseball player, and before you step up to the plate, you're imagining all of the different pitches that may come your way, right? So in this condition, it may seem like we're practicing explicitly planning sequences of movements so that we don't have to worry about these sort of cognitive processes when we have limited time. But it may be that planning at this level can engage the motor system and actually promote implicit adaptation, which doesn't seem so crazy when we consider that mental imagery actually engages processes involved in adaptation, as shown in this work from Daniel Wolpert's lab. And also doesn't seem so crazy when we consider the conventionally accepted framework for motor adaptation, in which a motor plan acts as input to a motor controller, which generates a motor command for the production of movement that is also sent to a forward model that takes that motor command as input and predicts the sensory consequences of that planned movement. These sensory predictions are compared with observations that arise from the movement to compute sensory prediction errors. And when that error is non-zero or observations don't conform with predictions, this sensory prediction error drives implicit adaptation to bring movements into line with our predictions. Notably, however, sensory prediction should proceed even when movements do not occur, right? So forward models are thought to predict the consequences of movement before relevant sensory information can reach the brain, indicating that this sensory prediction process occurs in parallel with and is not dependent on the performance of movements. So in the event that movements are canceled or interrupted, sensory predictions should still be computed, allowing observations based on other events in the world to potentially drive sensory prediction error computation. and thereby support implicit adaptation without actually performing a given movement. Leading us to our hypothesis that implicit adaptation may occur when plane movements are withheld. So in order to test this hypothesis, we need to evoke planing with and without movement. So to do so, we modified a visual motor reach adaptation task to be a stop signal task. So in standard trials with movement, which I'll refer to as Go trials throughout the rest of the talk, participants controlled the movement of a white cursor via their hand. The hand was occluded during the study, but it's shown in red here for visualization purposes. Additionally, a gray target was present throughout the duration of the task. When that target turned green, participants were instructed to reach directly through it, thereby recruiting planning of that reaching movement. But during the reach, cursor feedback was rotated relative to the hand trajectory, thereby inducing an error during the movement, as a standard again during these visual motor reach adaptation tasks. In our second trial type, we cued people to perform trials without movement, otherwise referred to as stop trials. So these trials began pretty much the same way as Go trials did. The Go cue is presented. However, 100 milliseconds later, the target turned magenta, indicating to participants that they should withhold their movements. And then with a delay determined by that participant's individual reaction times on previous trials, the cursor was shown moving past the target at an angle, thereby allowing us to present an error without the participant actually moving. Now, so this presents us with a little bit of a challenge to actually measure learning when movements don't occur on these trials. So we employed a triplet paradigm, allowing us to quantify adaptation even when movements do not co-occur with errors. So during a triplet or a set of 3 trials, we had participants reach towards targets without receiving any visual feedback on the first and the last trials of the triplet, thereby giving us a good measurement that's not contaminated by online control processes of what the pre-existing motor plan is for reaching towards that target. On the second trial of the triplet, we presented the Go or the Stop trial in order to present an error signal. And then we were able to measure single trial learning as the change between the reach angle on trial 1 and the reach angle on trial 2, and attribute that to the error viewed on trial 2. Since we use this paradigm, our measurement of learning here is this triplet-wise single trial learning, and we randomly varied the error directions in order to avoid saturation of learning during the task. Okay, so I've told you about how we're going to cue planning to occur even when movements are withheld. But in order to isolate implicit adaptation, we gave people instructions to ignore the cursor and aim straight for the target after previous work in the field. And furthermore, we attempted to maximize the amount of implicit adaptation that we would observe by presenting 15-degree errors, which have also previously been shown to saturate asymptotic learning during implicit adaptation. Okay, and as a little bit of a proof of principle, I'm going to show some evidence that stop trials actually successfully recruited planning. So on the x-axis here is the proportion of stop trials that any particular subject showed with movement. And on the y-axis is the number of subjects showing movement on that proportion of trials. And you can see that about half the time, on average, people are moving even when they're cued to withhold that response, suggesting that they're reliably planning to perform movements on these trials, and that we have a reasonable chance of activating the forward model and generating sensory predictions. Importantly, we've excluded these stop trials with movement from further analyses so that they don't contaminate our measurements of potential learning without movement. Okay, and now I'm going to show you some data about whether learning actually occurred during these triplets. So on this y-axis here, I'm showing single trial learning in degrees. On the left, you're going to see learning observed on Go triplets, and on the right, learning is observed on stop triplets. And as we can see, there is a reliable learning response in both conditions that proceeds opposite the direction of the observed error. Notably, there's a statistically significant difference between adaptation in both error directions within each movement condition, which is a hallmark piece of evidence for adaptation during this task. And I'd like to take a moment here to note that, or to really emphasize that it's remarkable that we observed learning actually under both conditions. And the degree of learning that we observed here is consistent with what has been observed in previous studies. So on the y-axis here is learning rate, and on the x-axis here I have labels from different studies that used similar rotation sizes. And in both the go and stop conditions, we see adaptation within or near the dynamic range that's been shown in previous work. However, notably, learning is actually smaller during these stop triplets, which I'll return to a little bit later in the discussion, but raises an important question about whether we can provide further evidence that learning on these go and stop triplets is actually supported by the same process if there are differences in the amount of learning observed. And one way that we can start to approach that is by examining whether the memories actually showed similar decay rates, right? Because we would imagine that similar learning processes should be retained at similar rates. And fortuitously, the triplet paradigm allows us a good way of quantifying retention. So following one triplet, there is a subsequent triplet that begins with a no feedback trial, allowing us the opportunity to measure memory decay in the absence of the presentation of other visual error cues. So we took the reach angle on the first trial of the first triplet and compared it with the reach angle on the first trial of the subsequent triplet to get a measure for this retained adaptation, and then took the ratio of the retained single trial learning over the initially observed single trial learning in order to quantify retention. So that value is shown on the y-axis here for both go and stop triplet conditions. And you can see that retention does not differ between the different triplet types, suggesting that memories show similar decay rates and they may be supported by the same process. But we can further address whether the degree of learning on go and stop triplets is related on an individual subject level. So on the x-axis here, we see individual subjects single trial learning on these go triplets, and on the y-axis, single trial learning on the stop triplets. And we can see that there is a significant correlation between the amount of learning that individual participants showed under each conditions, suggesting that while there may be some conditions that affect the degree of learning that we can see on these stop triplets, that they may be supported in principle by the same underlying process. But if we take a step back for a second and consider the experimental paradigm, we may come to think that the comparison between adaptation on go and stop triplets isn't really fair, especially during this rotational perturbation. So during the visual motor rotation, the participant reaches towards the target, as shown in this red arrow, and the cursor is rotated at a certain amount relative to that. However, if the participant reaches in a different direction, the cursor feedback will be shown in a, the same relative distance from the hand movement, but a different relative distance from the target location, which varies between the stop trials where, considering that there's no movement, we simply animated the cursor so it moved to a predetermined location. Under an arrow clamp perturbation regime, that wouldn't be the case, right? So if the person reached towards the target, the cursor would move towards a predetermined location. And similarly, if the participant reached away, thereby unifying the visual feedback between both of these conditions. So I'm going to show you some data from an arrow clamp version of the task that was conducted online with the same trial structure. However, we also included triplets with 0-degree perturbations to ensure that baseline performance was reliable in this online study. And we can see that we do observe reliable adaptation under both go and stop conditions. That is once again smaller in the stop triplets. In the interest of time, I'm not going to show you the replication of the retention or the correlation between adaptation and the go and stop conditions. But if you're interested in that or details of other online experiments, our preprint is available online on bioRxiv.
You have 5 minutes, Olivia.
Thank you. So in summary, I would like to highlight that we've demonstrated that movement is not necessary for implicit adaptation, which replicates across multiple conditions, including in the lab and online, as well as with a rotation perturbation on Go trials or an arrow clamp perturbation on Go trials. And furthermore, the learning that's observed under both of these conditions may be supported by the same underlying processes, as is suggested by the fact that we see similar levels of retention between those conditions. and related subject-wise degrees of single trial learning. Notably, we've also replicated that we see greater learning in the presence of movement than without movement, which may be attributable to imperfect timing of errors on stop trials. So I mentioned that we showed that cursor feedback with a relationship to an individual subject's previous reaction times, but in reality, we don't know the exact timing of the generation of motor plans on these stop trials. Or it could be attributable to the fact that we're missing appropriate proprioceptive components of feedback. Or alternately, there may be a role for internal versus external attribution of errors, as has been suggested by previous work. So I'd like to take a moment to step back to the model that I presented earlier and present this modification here that emphasizes that a causal link may not actually be required between movement and observation for us to be able to see or evoke implicit adaptation as a response to sensory prediction error computation. And with that, I'd like to take a second to thank you for your attention and your time. To once again highlight my co-authors, Alex and Sam. Alex, who made a really incredible contribution throughout this whole project and who has been instrumental to its execution, and Sam, who's been a really fantastic collaborator and co-author and has really contributed a lot as last author here. I'd also like to take a second to thank my colleagues in Jordan Taylor's lab at Princeton and also in Sam's lab at Yale, my funding sources, and to highlight my contact information if you want to ask me questions offline or provide feedback. Thank you so much.
All right, thank you, Olivia, for a really well-timed talk. So we have plenty of time for questions. And so we will start with Alkis. Alkis has a question regarding the failed stop triplets where they actually moved. So he's asking, was learning in the failed stop triplets closer to the one in go triplets or in stop triplets?
That's a good question. So the amount of learning in the stop triplets, I believe, so it varied a little bit between the different replications that we ran. But for the in-lab study, I believe it was actually more similar to adaptation on the stop triplets. So during this particular version of the task, we canceled the cursor feedback animation as soon as movement was detected. So they were only ever receiving partial feedback. Just for complete cleanliness of the interpretation, we excluded them completely from the analysis.
Okay, all right. Let's move on to the next question from Valeria. So she's saying, very nice work. How can you rule out that reactivation or action observation may be driving the effect you see instead of learning? That really a question of mine too.
Yeah, that's a really important question that we've been working on recently. So we ran a couple of pilot studies in which we instructed participants to simply watch the cursor move when the target turned pink. And we never presented a go cue at all, right? So the only thing people were presented with was a no-go cue. However, we still were observing movement on a substantial proportion of those trials, suggesting, perhaps in line with the data that Tim Carroll presented earlier, that something about the target presentation may necessarily trigger formation of some kind of motor plan or motor activation. So we're looking for a way to more cleanly address that, but certainly hope to address it soon.
Okay, all right, thank you. From Abigail Person, super cool. I'm curious about adaptation. Oh, great, sorry, it popped around. Curious about adaptation of the motor plan versus adaptation of the motor commands. Do you monitor EMG to determine covert action on stop trials or just over movement?
So we have not been monitoring the EMG or the EEG signals yet. We've been discussing that a little bit over the last couple of weeks as we get more things running in the lab. But yeah, right now I'm a little bit agnostic to it, which is related to why implicit adaptation is shown here as proceeding through this whole big box. I didn't want to make a strong claim about where adaptation actually occurs, but that's a really interesting and important point.
All right. And a question from Katinka. So thank you for this interesting work. do you think it's necessary to induce movement planning? To evoke, so this is similar to the observation question. Do you think it's necessary to induce movement planning to evoke adaptation? That is, could a participant adapt just by seeing the errors? Or have you thought of doing that experiment?
Yeah, I guess just to speak to that a little bit more, since we talked about it slightly before. At this point, we can't conclusively say that the motor plan is really necessary for this process. So the inspiration for this project and hypothesis did come from considering a framework where motor plans were driving adaptation, but it's not necessary here, right? And there's work notably from Paul Gribel's lab that indicates that adaptation can actually occur due to observation of other people performing the task. So the experiments here differ somewhat from what they did. So in the Gribel lab work, people viewed videos of people like reaching through force fields. And I believe that the participants could see the cursor feedback as well as the arm movement. Whereas here, people are only able to see cursor feedback. So it's tempting to speculate that this motor plan may serve as a substitute for the observation of a participant's, somebody else's movements, and as a basis for computing a sensory prediction error without having to infer what an agent's particular goals were. I hope that was clear.
No, I think it was. All right, so let's see. We still have some more time. So from Jonathan, thanks, Olivia. If there was EMG activity on stop signal trials, would that affect your interpretation of your results?
Yeah, so I think that's pretty interesting. It seems quite likely that we would see EMG activity on stop trials, at least as far as it pertains to the onset of the target, as related to the short latency responses that were discussed earlier today. However, the origin of those signals may or may not be sufficient to activate the forward model and generate sensory predictions or otherwise support error computation. So I think that is a super interesting question that I'm, I guess, a little bit afraid to make too strong of a claim about.
Right.
But nonetheless, I just wanted to highlight that nonetheless, and conceptually, one thing that is important here is that we're seeing adaptations of the whole movement, right? That is not performed on stop trials, right? So even though there may be some lower level of muscle activation, we're still getting learning as it relates to movements that are not technically performed themselves.
All right, that's great. Well, thank you so much, Olivia, for that really interesting talk. And now we're going to move on to our second talk of this session. And so that is Takuji. Great, you're getting ready. So the title of the next talk is Shifts in Neural Preferred Directions Predicts Systematic Changes in Rate of Motor Learning. Right, Takuji, you can take it away.
Thank you very much. My name is Takuji Hayashi, and I'm a postdoctoral fellow in the Smith Lab at Harvard. The title of my talk is Shifts in Neural Preferred Directions Predict Systematic Changes in the Rate of Motor Learning. So many studies have investigated human motor learning. Some try to find how motor learning changes behavior. Some try to discover the neural mechanisms of learning and how neural representations are changed. And others develop improved computation models for motor learning. In general, these studies aim to advance our understanding of how motor learning affects our actions. A relatively smaller number of studies have investigated another feature of motor learning, how motor learning can change ability to learn in the future. This ability has sometimes been termed learning to learn, but we know very little about its neural underpinnings. Here, we hypothesize a straightforward neural mechanism that can increase or decrease single trial learning rates by a full 50%, and we provide experimental evidence that is consistent with its predictions. Neurons in M1 are thought to have specific representations of movements. Many studies examined horizontal arm reaching movements during neural recordings in monkeys and found that neurons in M1 display broadly tuned cosine-like patterns of activation across different movement directions. The activities of these representative neurons from a study of Jog Poras et al. In 1982 was highest when the monkey reached in this 135 degrees direction, but smallest when the monkey reached in this 315 degrees direction. If you look at the pattern activity across different reach directions, we can see clear direction-dependent tuning, and the direction where the highest activity takes place is generally called the preferred direction. Interestingly, modal learning is known to change this neural representation. In particular, after adapting to dynamic force field perturbation or kinematic visual modal perturbation, the PD is systematically rotated. For example, the preferred direction of this example neurons rotated clockwise from 160 degrees to about 120 degrees after clockwise force field learning. The PD rotation is thought to reflect changes in motor actions. If clockwise force field perturbation is applied, reaching towards the frontal target requires you to generate additional leftward directed motor commands. So neurons that produce leftward force should be more active during forward reaching movement. That's why the direction of peak activity, that is a preferred direction, is rotated in the clockwise direction after clockwise force field. The PD rotation appears to be a general feature in motor cortical areas, such as M1 premotor cortex and supplemental motor cortex. The key idea behind the current project is that the process of PD rotation should systematically influence the subsequent motor line. We'll go through a sketch that lays out the mechanism for this. To start, this figure shows neural activity across movement direction represented by local tuning curves. Each neural unit plotted has different PD, and PDs have been found to be mostly uniformly distributed across each direction as pictured. However, consistent with the fact that the learning of force fields and visual motor perturbation is local to the trained target directions, PD rotations have also been found to be local. And interestingly, when PD rotation occurs, the locality of PD rotation would lead to an increased density in the PD distribution in the area to which the local rotation occurs here. And at the same time, an increased sparsity in the PD rotation in the area from which the local rotation occurs here. Critically, these changes in PD density would systematically alter the number of these units that are actuated for movements in different reach direction. In particular, there would be a great number of these neurons actuated for reach direction with increased PD density, and a smaller number of neurons actuated for reach directions with decreased PD density. Therefore, if these units themselves or downstream consequences of their activity were involved in subsequent motor learning, and then learning ability should be enhanced for target direction with increased PD density, and it should be reduced for target directions with decreased PD density. We suggest that the plasticity behind slower, more gradual learning primarily takes place upstream of neurons that show PD rotations, as such plasticity must be responsible for any observed PD rotation. However, rapid single trial learning will primarily occur at or downstream of areas where PD rotation is present, resulting in the systematic modulation of single trial learning rates. A simple computation model would support this idea. In particular, a basic model primitive framework would yield a model learning rate for each movement direction that is proportional to the number of units activated for the direction. For example, if you intended to make a movement towards a minus 30 degrees visual target, not all model primitives, but primitives which have PD close to minus 30 degrees are activated. And then model command would be produced by a weighted sum of the model primitive activities. If error is produced by an external perturbation, the weights corresponding to those model primitives are largely updated. So consistent with our idea, total model primitive activity, which is proportional to the number of actuated units, determines the amount of learning that each error elicits. Thus, changes in the PD distribution should directly influence motor learning sensitivity. I started building more specific prediction to be validated with a behavior experiment. Consider simple region movements. We can accurately perform a region movement in any direction since we have an accurate visual model mapping that transforms the visual target location in any direction into a set of motor commands that will reach the target. The ability to move in any direction corresponds to the existence of neurons with PDs distributed across all movement directions. Thus, PDs cover all locations in the visual model mapping, and the PDs are thought to be fairly uniformly distributed at baseline like this. However, motor learning is known to distort the visual model mapping. Visual model rotation, VMR, is a directional perturbation where the cursor motion is skewed from hand motion. To correct the error, hand motion must be skewed in the opposite direction. Importantly, the model learning effects are locally generalized and thus deform the visual model mapping like this. This example assumes Gaussian-like generalization for 80% motor learning over 30 degrees VMR with 30 degrees width. Based on neurophysiologic findings, we know that the preferred target directions of neurons in motor cortical areas are rotated due to motor learning, as these cells consistently code not target but movement direction. Critically, this corresponds to a horizontal shift on this visual model mapping plot for cells local to trained target direction. These horizontal shifts change the density of the preferred target direction distribution with an increase in density in the negative target direction here to which the PD rotation occurs, but a decrease in the density in the positive target direction away from which the PD rotation occurs here. Therefore, VMR training transforms isotropic distribution of PDs at baseline into an anisotropic distribution following training. Note that analytically, it is a gradient of visual model mapping that determines the relative changes of PD density as a global shift in the overall mapping that would maintain its slope will preserve uniform PD density. So specifically, we can predict that after 30 degrees VMR training, the PD distribution will be 50% denser in the negative target direction and 50% less dense in the positive target direction for an expected adaptation level of 80%. And as adaptive plasticity at or below the levels of neuron displaying would be proportionately increased or decreased, we would correspondingly predict a pattern of learning rate increase and decrease of up to 50% each. That matches a biphasic pattern that should be displayed in PD density changes. We designed a behavior experiment to determine whether the direction-dependent modulation of motor learning rates predicted by PD rotation-based density changes is present in human motor learning. 22 participants performed simple point-to-point region movement to 10 different target directions during a baseline period, where we measured single trial learning rates, and were then trained on a counterbalanced clockwise or counterclockwise 30 degrees VMR in a single target direction, 0 degrees. Half of participants were trained on a 30 degrees clockwise VMR and half on a 30 degrees counterclockwise VMR. The VMR was gradually introduced during the training block at the rate of just 0.25 degrees per trial. And then after this 120 trial run, maintained at 30 degrees for 200 trials. After this training period, there was a longer 950 trial block where we interspersed measurement of single trial learning rate and 30 degrees VMR top-up trials to ensure maintenance of the trained adaptation. This mirrored the pre-training block that was identical, except that the corresponding top-up trial there displayed no rotation. In both the pre-training and post-training block, we measured single trial learning rates 30 times each for 10 different target directions in pseudo-random order. In the perturbation trial, we introduced a cursor clamping perturbation wherein the cursor path was constrained to a path that was directed either plus or minus 7.5 degrees away from the test target. We then measured single trial learning rate by determining the changes in the hand motion from before to after the 7.5 degrees elevation. We began by examining the visual motor remapping induced by the VMR training in our dataset. We found this remapping to be consistent with previous studies and with our prediction for it. The generalization for the clockwise training group shown here was well modeled by Gaussian shape distortion, which accounted for 89% of variance in the change from the baseline mapping. The best fit Gaussian had a height of 77% of trained 30-degree VMR compared to the 80% expected, and a sigma of 31 degrees compared to the 30 degrees expected. The observed remapping would correspond to a sizable increase in PD density for negative target direction and a sizable decrease for positive target directions. And this would predict a corresponding bimodal pattern for changes in single trial learning rate.
Could you have 5 minutes?
In contrast, the counterclockwise training group shows opposite changes in visual model mapping, consistent with PD's shift in the opposite direction compared with clockwise training group. However, like the clockwise group, the observed remapping was highly consistent with previous studies and with our prediction for it, with a Gaussian fit accounting for 97% of the variance. This remapping predicts an opposite pattern changes in PD density compared to the clockwise training group. Here, PD density should increase for positive target direction, but decrease for negative target direction. And this would again predict the corresponding bimodal pattern for changes in single trial learning rate. Now let's look at whether single trial learning rate changed between the pre-training data and post-training data across target directions. Our model predicts an asymmetric pattern for these changes, with increased single trial learning rates for negative target direction and decreased rates for positive direction. Remarkably, for the clockwise group, the data appear to show increase in the learning rate in negative target directions, but decrease in the learning rate in positive target direction, in line with this prediction. The counterclockwise group data, our model predicts the opposite pattern result with decreased single trial learning rates for negative target direction and increased learning rates for positive directions. We find that again, the data shown in blue were at the prediction, with changing in learning rate that displays the opposite pattern to that observed in the red clockwise data when plotted against low target direction. If we align the prediction for the two groups by plotting the data against target direction with respect to the training direction, which flips counterclockwise training data, then the combined data closely resembles predicted pattern of biphasic modulation. The combined data clearly shows the predicted pattern of biphasic modulation. Correspondingly, we find a highly significant 80% positive correlation between this green line, indicating the gradient of acquired visual model mapping, suggests that the predicted biphasic shape. Additionally, we find that the learning rates in region 1 are significantly increased, the learning rates in region 2 are significantly decreased, and the learning rates between region 1 and region 2 shows a highly significant differences as predicted by the PD density-based model. The results suggest that single trial model learning rate is successfully predicted by estimated PD density. We next examine extent to which the trained BMR was learned via implicit versus explicit adaptation. We designed the experiment to promote implicit learning by providing real-time cross feedback, ramping up the perturbation very gradually, and instructing participants to aim directly at each target. To assess implicit versus explicit learning, we examined shifts in the center of the generalization functions separately for the counterclockwise and clockwise groups, as previous work has shown that the learning effects are generalized around the direction of explicit strategy rather than training target direction. Thus, for counterclockwise data, full explicit learning would predict a minus 30 degrees shift in the generalization, whereas full implicit would predict a 0 degrees shift. The data showed a minus 2 degrees shift that was not significantly different from 0. Now for the clockwise data, full explicit learning would predict a plus 30-degree shift in the generalization, whereas full implicit would again predict a 0-degree shift. Here, the data showed a minus 4 degrees shift that was nominally in the wrong direction for explicit strategy. And again, not significantly different from zero. So together, the data suggests that there little to no explicit contribution to the adaptations that were trained. In conclusion, we first theorized the local model learning would result in a specific pattern of anisotropic changes of PD density based on distortions in the visual model mapping. We then hypothesized that these changes in PD distribution would predict systematic direction-dependent changes in the rate of single trial model learning. And we found that these predictions were borne out by experimental measurements of single trial learning. Therefore, we show that PD rotations that underlie model learning can result in dramatic changes in the ability of the model system to learn from subsequent model errors. I appreciate that Professor Maurice Smith, Professor Daichi Nozaki, Professor Ken Takiyama, and the students and postdoc gave helpful advices and comments. I also thank the foundation giving me an opportunity to do this study. Thank you very much.
All right, thank you so much for that, that great talk. And there are a couple questions. So from Jordan Taylor, great talk. How do you know that the effect couldn't be driven by use-dependent learning rather than a change in PD distribution? Or do you think those are the same?
So in this experiment, I don't think the use-dependent learning can explain our results because in the experiment, participants mostly performed reaching movement towards minus 30 degrees or plus 30 degrees direction because in the VMR training trials. So if the use-dependent learning is important and then the learning is higher when the cursor clamping perturbation is when the cursor clamping perturbation is opposite to the direction. For example, if you make a movement in plus 30 degrees direction, and then if you are exposed to the cursor clamping perturbation in minus that in this direction, then single trial learning higher. However, the cursor clamping perturbation is negative this direction, and then single trial model learning rate should be small. And combined these data, I did see the combined data for both directions. And so if the use-dependent learning is important, and then I expect that we cannot get any like bimodal modulation.
Yeah. All right, let's, Jonathan has a question. Beautiful results, Takuji. Professor Denise Henrich's lab has found that one sense of hand position is also distorted locally where the rotation was presented. So could the remapping be in sensory or proprioceptive map rather than in motor units, as you propose?
Well, yeah, it's probably important it's important, and it could change the visual, the single trial learning rate. But I don't know why. Actually, I don't know why this happens, the bimodal distribution, bimodal modulation. So yes, that's a very good comment. I will think about it more.
All right, and if you remember anything, you can also follow up in the Q&A box.
Okay,
I have a
you.
question. It seems from your plots, so you see both an increase in learning rate on one side and then a decrease in learning rate in the other, if I understand correctly. And it seems that for both directions, that the increase and the decrease are not of the same. So it's not fully symmetric. It seems like your increase in learning rate is stronger than your decrease in learning rate. And I was wondering if that was indeed the case, and also whether you have any explanation for it.
I think this is because of the noise of measurement of single-choice learning rate. Because single-choice learning rate is very noisy, which is the noise level is very, comparable to the actual noise in model commands. So we have to get usually a lot of trials to see that, to rigorously see the single-choice learning rate. However, we couldn't do that because you have to get, single-choice learning rate before and after training for 10 different targets. So it needs 20 times more. So I think this is because this shape is not beautiful actually, but it's because of the noise of measurement.
But your model would specifically predict that they should be symmetric changes.
Yes.
Well, we have time for one quick last question from Valeria. To what do you attribute the difference in the percentage change of motor learning you find between the clockwise and the counterclockwise rotations?
So do you mean this data? Let's say again.
Perhaps. Valeria? Right. I mean, there is a difference, correct? Yes, she's saying yes.
I'm not, totally.
To what do you attribute the difference in the percentage change of motor learning that you find between the clockwise and counterclockwise rotations? Well, perhaps in the interest of time, we can take this offline. We'll leave this in the chat so we can move on to the
yes, I will.
Our next talk. Sound good?
Yes.
All right. Okay. Well, thank you very much for a
Thank you so much.
Intriguing talk. Really cool design. Okay, so with that, I'm going to hand it off to Adrian, who's going to introduce our next speaker.
Thanks, Alea. Yes, it's my great pleasure to introduce our final speaker for today, Jennifer Collinger from the University of Pittsburgh. Jennifer really is a pioneer in developing brain-computer interfaces in humans, and particularly the use of bidirectional BCIs, where not only brain activity drives movement of a prosthesis, but the prosthesis also sends back information back to the brain. So I'm very excited to hear Jennifer's talk. Over to you, Jennifer.
Thank you. I'll share my screen. Okay, so look okay. All right. Well, yeah, thank you very much for having me here to talk about our work related to brain-computer interface development. I know that it's a little bit more applied than some of the talks that we've been hearing about today, but I'm excited to tell you about our results about the influence of sensory feedback on BCI control of grasp. So in our lab, we're really interested in taking what we know about the way that motor cortex participates in the control of movement and trying to use that to restore function for people with spinal cord injury. So in the United States alone, there's about 17,000 people per year who sustain a spinal cord injury, and there's about 300,000 people living with spinal cord injury in the United States. These injuries tend to occur fairly early in life. The average age of onset of injury is 43 years old. And so it's really important to try to restore function either through rehabilitation or in the case where that recovery plateaus through technologies such as brain-computer interfaces. You can see at the right that the level of injury impacts the amount of function that people have after injury. And we're working with people who have cervical level spinal cord injuries. So up here in the cervical spine, that impacts their ability to use their arms and hands to interact with their environment. And more than half, about 60% of injuries are in this area of the spinal cord. There was a study done a number of years ago by Kim Anderson that's, where she famously asked people with spinal cord injury, particularly with tetraplegia, which of these functions listed along the bottom here, if restored, would have the biggest impact on their quality of life. And by far, for people with tetraplegia, restoration of arm and hand function is their top priority. And so our group and others think that brain-computer interfaces can be used to try to tap into brain activity that remains intact after a spinal cord injury, bridge that injury in the spinal cord, and try to restore movement through some type of assistive effector. In our lab, we use a robotic arm right now to really try to understand how much information we can record from motor cortex and what type of performance we can get. We use a bidirectional BCI, and I'll walk you through the major components of that in this diagram here. So if we start in the motor cortex, shown here in blue, we implant intracortical electrode arrays to record activity from the motor cortex. We decode the patterns of activity that are observed across those, about 200 channels of recording, and turn that into a control signal for a robotic arm. And I'll talk to you a little bit about some of those details in the upcoming slides. At the same time, we can record from sensors in the robotic hand to understand the interaction forces that are being experienced by the fingers in the robot. And we can turn that into stimulation patterns through electrode arrays that are implanted in area 1 of somatosensory cortex, shown here in red. And so this area typically receives tactile input from the periphery, and that's our goal, is to try to restore that tactile input to people with spinal cord injury. So even though we've had 3 participants in our study at the University of Pittsburgh, as well as 1 at the University of Chicago, who is now part of our clinical trial, but most of the results that I'll be talking about today really come from 1 participant who was a 28-year-old man at the time of his implant. He had a spinal cord injury at C5, C6. It was an Asia B incomplete injury. And so what that meant for him is that he really had no ability to move his hands or fingers, but he did retain some proximal function of his elbow and shoulder, for example. The devices that he had implanted were, he had 2 of these 88 channel.
Good afternoon, sorry.
He had 2 of these 88 channel arrays implanted in motor cortex. You can see the wiring pattern up here. Most of the electrodes in the center were wired, and 2 smaller 32 channel electrode arrays implanted in somatosensory cortex. And these wiring patterns and channel counts are really just dictated by the connectors that we use. So each of them had 128 channels. So we tried to maximize the coverage within each of these arrays. If we start on the recording side, we use the Utah array by Blackrock Neurotech. You can see here. So each of these electrode arrays has 100 electrode tips, and we implant those in motor cortex. If we look at the recordings, in case you're not familiar with these devices, essentially each of these black boxes is representing the recordings from 1 electrode array, where each threshold crossing or action potential that we measure on that channel is shown as one of these white traces. And we can zoom in here and see that, on this particular channel, we're actually able to measure activity from 2 single neurons, but a lot of times we're just measuring more multi-unit activity from nearby neurons that are nearby to the electrode tip. And what we really care about for these recordings is the firing rate and how that correlates to movement. So our participants have paralysis. They're not necessarily able to move to allow us to figure out the relationship between brain activity and movement parameters. So we use an observation-based calibration paradigm. And what that means is that the first step of that calibration is that they watch this virtual robotic arm reach to a target shown here in red. They're instructed to grasp it, to carry it to a new location and orientation indicated by this planar target. They reach that, and then they're cued to release. And throughout this entire movement, they move to objects that are randomly placed throughout the workspace. We record both the kinematics of the robot that are under computer control initially, as well as the firing rate of all of the neurons in motor cortex. And so we can build an initial decoder or essentially a map from those firing rate patterns onto movement parameters. And in our case, we typically control the endpoint velocity, both in Cartesian extrinsic space of the hand. So we can do 3-dimensional translation, 3-dimensional orientation or yaw pitch roll of the hand, and then opening and closing of the digits or even multiple hand shapes. And so what many people have shown is that these attempted or imagined movements really generate similar neural activity patterns to what we see during overt movements. And when I say similar, what I mean is that, when people have measured from monkeys reaching to different targets, even as we saw in the last talk, right, these neurons have a preferred direction where the firing rate is correlated to the movement direction and velocity. And we see those same relationships hold true even in imagined movement in someone with paralysis. And so I won't focus too much on the motor control part. This is something that we've been doing for a number of years, as well as other groups. But what I'll show you is, this is actually our first participant who is using the BCI to control this robotic arm with 7 degrees of freedom. So 3D translation, 3D orientation, and opening and closing of all the fingers is 1 unit of grasp. And here her instruction was to just pick up the object, put it on the shelf, and put it back down on the table. And so what you can see is that she's really, able to generate fairly fluid movements. She's not thinking about explicit sort of stepwise commands. She's really thinking about the goal of that object, and even navigating back down from the shelf, she was sort of able to picture the configuration of the wrist that she needed in order to avoid hitting the robot on the shelf. And so we're able to, by having participants imagine just over, about a 5 to 10 minute calibration period, they can start to use this brain-computer interface that picks up on these fairly natural and, we like to say biomimetic or bio-inspired movement patterns that we can record from motor cortex, even after chronic spinal cord injury. And so even though I didn't talk too much about this motor control, that video does demonstrate that she has fairly good control over the robotic arm. She can pick up objects and move them around. So why do we even need sensory feedback? Of course, we've seen that people who have sensory deficits have impaired movements, particularly as we think about more dexterous tasks, right? Like buttoning a button, tying a shoelace, brushing your teeth. That relies heavily on the tactile and proprioceptive inputs from your hands and your joints in order to execute those movements. We're still trying to figure out how we can control that level of dexterity with a BCI, but even for more simple movements, tactile cues and these signals of state transitions are really often typically conveyed by tactile input. So whether it's holding onto a cup so that you don't drop it or change the orientation, particularly handing an object to another person, the timing and coordination of that action is really driven by the cues from tactile inputs in the periphery. And same thing, if you're trying to grab a fragile object, you need to know how much force you're applying so that you don't exceed that force and break the object. So we've explored trying to use intracortical microstimulation of somatosensory cortex in order to generate tactile sensations after spinal cord injury. And this work that I'll be talking about was really led by Charlene Fletcher, who was a grad student at the time in our lab, and also my colleague, Rob Gaunt, who's really been leading a lot of the sensory restoration efforts in our research group. And so just to summarize what we found, first, let's look at the schematic of these arrays. So the central sulcus is marked here in red, and then we're showing these 2 different arrays. Each of the boxes represents one of the electrode tips. The gray boxes aren't wired for the reasons I mentioned earlier, but the colors in these electrodes correspond to, when we stimulate through this particular electrode, where does the participant report feeling it? So first of all, he reports feeling it as if it's coming from his own hand. And for this particular electrode, it feels like it's coming from somewhere at the base of his pinky finger. And as we move more laterally, we start to see that we generate sensations on the ring finger in green. And then even more laterally is the middle finger. And then for the lateral array, it was primarily generating sensations on the index finger. So this lines up with the expected somatotopy or spatial organization in sensory cortex that's been observed, in intact animals and humans and, in the literature for many, many years. And so again, we would expect that the index finger was more lateral, and then as you move more medially, moving towards the little finger. And so we place these arrays based on pre-surgical imaging of imagined touch and imagined movement. And we found that stimulation through these electrodes generated sensations in the expected area, even in somebody who was 10 years post-spinal cord injury. These projected field locations, so where we elicit these sensations, are very stable over the periods of weeks or months or even years. So what I'm showing you here is the same schematic for the medial array on top, the lateral array on bottom, as we progressed through about 4 years of implant here. What you see is that it took some time for the participant to be able to feel these sensations that were elicited from ICMS. But once he was able to feel them, they became relatively stable. So we test this, in a randomized order on multiple days. And we see that, it's remarkably stable and that these lateral electrodes are generating sensations on the index finger, and then the middle ring and pinky tend to be more on the medial array. So besides being, focal and feeling like they come from a particular part of the body or particular finger, we also need to be able to convey useful information about the task that the participants are performing. And so we had an inclination from animal experiments that have been done before that, increasing the stimulation amplitude should increase the perceived intensity of the sensation that was evoked. And so we were able to demonstrate that that was true, again, in a person with spinal cord injury, where here you're seeing the results for a single electrode. Stimulation amplitude is along the x-axis, the reported magnitude is along the y-axis, and we see a very linear relationship between those things. And this held true across multiple electrodes as shown by the group data. So this is really useful to us. We know that we can convey information about the amount of force. Just maybe as a teaser, we've also explored trying to change the frequency of stimulation. And there we see that the results are much more complex. It seems to impact every electrode in a slightly different way. And so Rob and his students are really trying to understand if there's any guiding principles that might predict why an electrode would respond to changes in frequency in a different way. But for the reason we tend to modulate amplitude to convey information just because that response is very predictable across electrodes. So obviously a big question that people wanted to know the answer to as we transitioned into human studies was, what does intracortical microstimulation feel like? And that's been across all of the neuroprosthetics literature. It's actually become apparent that it's difficult to quantify and to describe these sensations that are really not like anything that the person has ever felt before. So even though they do feel like they're coming from their own hand, it's not necessarily completely natural. It's an incomplete restoration of touch for sure. And so as a first pass, we asked them, how natural does it feel on a 1 to 5 Likert scale? The response is typically a 4. So possibly natural, almost all of the time. It's never been painful. If we look at the descriptors that are used to describe these sensations, about half the time it's more of a pressure sensation, but a quarter of the time it's more of a tingle. We also get some electrical or warm descriptors for these sensations. And so we tried to see if we could reproduce that through things that any of us might have experienced. So we've tried using transcutaneous electrical stimulation on sensate parts of his skin, like on his arm. And he describes that as feeling extremely different even than these electrical sensations that are reported with ICMS. For some of these pressure sensations, mechanical indentations or just pushing on the skin with a Q-tip feels pretty much the same. And if we play the stimulation in short bursts of trains, we can generate sensations that feel like tapping. So the next step, now that we kind of had studied motor control, by itself, and then characterize some of the responses to ICMS, was obviously to put them together to see if having that sensory feedback can improve BCI control. So this kind of walks you through the setup for this particular experiment. Again, Charlene was leading the sensory feedback aspects of this project along with Rob Gaunt. John Downey, who was a graduate student at the time and is now at University of Chicago, was leading the motor control. And Jeff Weiss is an engineer in our lab who was really trying to make sure that all of this software was working together, that we were rejecting stimulation artifacts and could record and could actually perform online control with ICMS. So in this experiment, again, we're recording from motor cortex. The control of the robotic arm here was in 5-dimensional space. So 3D translation, pronation and supination of the wrist, and then opening and closing the fingers as a group. We're recording the neural activity to decode the endpoint velocity in those 5 dimensions. For the sensory feedback side, we're actually measuring the torque using sensors in the motors at the base of the fingers. And then that torque was mapped onto stimulation amplitude in a linear fashion as shown here for an electrode that corresponding to the proper finger. So the index finger torque caused stimulation of an index finger electrode. The primary task that we used to quantify performance was the action research arm test. It's a outcome measure that's commonly used after stroke to measure unilateral arm impairment and recovery during rehabilitation. And we selected 9 of these objects that we've been using in our studies for a number of years, where they needed to pick up 4 different size cubes, a sphere, a rock, and 2 different cylinders. And the goal is to pick up the object, place it on a raised platform as quickly as possible. Each day they were given 3 attempts where we scored that from 0 to 3, where 0 means that no movement was possible, which really didn't ever happen. 1, that the task was partially completed, meaning that they could at least touch the object. 2 means that they were able to complete that entire movement in less than 2 minutes. And 3 means that they could complete it in less than 5 seconds. And 5 seconds is considered, a normal able-bodied completion time for this task. We did record completion times for all of the trials. So the main take home that I want to share with you is that ICMS improves performance. And so the first way that we look at this, again, you can see this task over here, the picking up the object, placing it on the raised platform. The first way that we looked at this was really the score of that object. And so we had been doing experiments with this participant for 2 years prior to doing these bidirectional studies. Almost all of the time we were completing these tasks without ICMS. On occasion, we piloted some different ICMS mappings, but in general, for 2 years of doing these experiments, his mean score was an 18. So if you remember the scoring, that means that typically he was completing most of these objects correctly, but it was in that somewhere between 5 seconds and 2 minute range. He wasn't breaking that 5-second barrier too often. As soon as we added in ICMS in the way that I described to you with that somatotopically matched feedback, for the next 4 sessions, his performance improved to a mean score of 21. And so again, in this case, that means that he was completing some of these objects in under that 5-second time. And now for the next 4 sessions, the only thing that we did was essentially take away the ICMS feedback. The decoding, calibration, visual feedback was all the same. And his performance dropped back down to what it was prior to any of these experiments. So the median score was a 17 here. If we want to get into the details a little bit to see why did that score improve, one way to do that is to look at the distribution of completion times for all of these trials. And so here I'm showing you a histogram of the trial times for all of the successful object transfers here. And without ICMS, we had a median of about 21 seconds. And what you see here is that there's only 1 trial that was completed in under that 5-second completion time. When we add ICMS, completion time was cut in half as far as the median goes to 10.2 seconds. You can see there's a clear shift of the histogram towards the left, towards lower completion times. There's much less variability reflected in the interquartile range here. And also, on nearly 20% of the trials, he was able to complete it in that able-bodied completion time. And so even though he'd been practicing this task for over 2 years at a fairly high level of performance, we saw quite a dramatic improvement where he was able to cut these times in half. So the next question that we asked was, what about his performance was improving? Was it really related to the sensory feedback that we were providing? So we broke that ERA task into 3 different phases. The first phase was the reach phase. So from the trial start to the time of object contact, we did see that he was moving a little bit quicker towards the target, but only about a half a second faster. The biggest performance improvement, though, came during grasp. And so grasp here was defined from that time of initial contact to the time of object liftoff. And so, many times, particularly when he didn't have ICMS, he was repositioning the hand so that he could get a stable grasp, or he would make an attempt to grasp and the object would slip out of his fingers. So this is where we saw the biggest improvement. So from a median of 13.3 seconds down to 4.6 on average with ICMS. And again, during the transport phase, we saw a very minor improvement in performance here where he was able to transfer the object to the raised surface slightly faster, but less than a second on average. So again, the majority of the improvement came really from that time of exploring the object and trying to pick it up and maintain a stable grasp. I think that the best way to maybe show this is to just play a video of side-by-side comparison. And so what you'll see here is the fastest trial for each of these objects with sensory feedback on the left, without sensory feedback on the right. And so he's already done with the trial on the left, but with stimulation, took him a little bit of time to get the fingers lined up properly. So same thing here, he's able to confidently pick it up on the left, not too bad on the right. For the sphere with sensory feedback, again, goes right to it without stimulation, is trying to make sure that the fingers are lined up. So again, he has visual feedback. It's just that he doesn't have complete vision of where those fingers are in contact with the object. So again, here his hand's not quite in the right orientation for picking that up, but he's able to pinch it between his thumb. So just to summarize, we've shown that a brain-computer interface can enable a high degree of freedom robotic arm control even after chronic paralysis. So using that observation-based calibration, we can restore these movements with very little training once the participants begin to use the system. We also showed that intracortical microstimulation of sensory cortex can evoke tactile percepts, again, after chronic spinal cord injury that are focal and aligned with the expected somatotopy. These percepts are stable for many years and can be graded in intensity by changing stimulation amplitude. And then critically, adding that tactile feedback to the BCI of motor control can significantly improve BCI controlled grasping. And so the next steps in our lab are really to try to understand how can we use the activity in motor cortex to control more dexterous movements? So the control of force at the hand, for example, even multiple dimensions of force control, and to continue to iterate on the sensory feedback aspects to again make it more biomimetic and useful. So with that, I'd like to acknowledge the large team of people who've contributed to this work. I mentioned already Charlene Flesher and John Downey, who contributed to the bidirectional study, as well as Jeff Weiss. My faculty collaborators at Pitt, Rob Gaunt leading the sensory feedback aspects of the project, and Mike Boninger is the clinical PI on the overall clinical trial. And thank you to our funding sources at NIH and DARPA. And of course, the biggest thanks to our study participants who, we obviously couldn't do this study without, but they have these devices implanted to help us do this work and develop this technology, and then are really committed to coming into the lab multiple times per week to work with us. So thank you to them, and I'll take any questions.
Thank you very much. I'll start with a question, actually. To what extent do you think it matters how realistic the feedback they're getting is? So you showed that you can't really elicit a sensation on the fingertips, even though that seems like the most, where they would perhaps naturally feel it the most, instead it's at the base of the fingers. Can they just learn some arbitrary stimulation and learn to use that? Or does it matter that it's naturalistic?
Yeah, I mean, I think it's probably a gradation, and I don't know exactly where that line is. So yes, we are, in this participant anyways, eliciting sensations more at the base of the fingers, and there's probably a couple of potential reasons for why that is. One is just potentially that, area 1 has an organization also in the medial to lateral, or in the anterior posterior direction from base to tip. And so we might just be at the base of the fingers. But what I would say is that in our study, they didn't really need to learn to use it. So we saw from the very first trial, from the very first day of using this, we saw an improvement in performance. There have been studies, for example, in Flip Sabi's lab, trying to stimulate in area 3A to restore proprioceptive input. So again, it's in the right area, but they don't have the luxury of asking the monkey, what does this feel like when we stimulate, right? And it took, in that case, hundreds or thousands of trials for the animals to learn to use this feedback to improve their performance. So it certainly seems like it needs to be task relevant to avoid that long learning, but exactly how, task relevant, I'm not sure.
Okay, thanks. So Zachary Danziger asks, would the tactile feedback be just as effective if you had, for example, LEDs emitting lights on the robotic hand with the intensity in proportion to the force, rather than doing it via ICMS? So does that matter? Is the neural, delivering it neurally important or not?
Yeah, and people have done studies with prosthetic control and other forms of sensory substitution, whether it's LEDs or vibrotactile performance. And I think for fairly straightforward tasks like this, they can learn that fairly quickly. And so here, I think our goal was to demonstrate, at least in a basic task, that this information was useful, didn't actually impair performance, and to some extent, was able to improve it, because as we think towards more complex tasks, I don't think that simple, light or vibrotactile cues will be able to convey that level of information.
So Firas Mawase asks, great talk, Jennifer. What about the sensation of the thumb? The thumb is highly involved in the grasping part of the ARAT.
Yeah. And so in this participant, we weren't able to really generate sensations in the thumb until a little bit later in the study, and those tended to co-occur with index finger sensations. We had an indication of where the thumb representation was based on the pre-surgical imaging, but there was a large vessel during surgery, and so we were unable to place an electrode array there. I certainly think that for more coordinated patterns of activity, it may be important to restore that function, although to some level it's going to be a little bit redundant, particularly for grasp, simple grasp tasks, because the thumb is going to just oppose the force of the digits. And I'm not sure that for at least a simple task like this, that it would provide additional information.
So Chris Mile asks, would stimulation of multiple electrodes rather than just through one provide a better sense of magnitude?
So more of a spatial activation pattern. Yeah, I think that's typically the way that, if you look at sensory responses to peripheral inputs, that is typically the way that is encoded. And so you see more of an increase in the spatial extent of neurons that are responding when the force increases at the digit. And that's partially because there's greater deformation of the skin as well. So it's over a greater spatial area. We've explored that a little bit. I think that we're fortunate in that if you increase the stimulation amplitude, it's going to inherently activate a larger area of cortex. And so to some level, we're replicating that now. But Rob's definitely investigating whether more spatiotemporal patterning of the electrodes is more natural.
So Tara Iwama asks, says, thank you for this stimulating talk. Not clear if the pun's intended or not. I wonder whether the motor function of the paralyzed hand changed after BCI training. Doesn't training affect motor function of hand that can be reorganized by BCI use?
Yeah, we did not observe that in our study. Here we're controlling a robotic arm. And so even though we are providing some limited sensory feedback of the tactile inputs, I don't know that we're closing the loop in the same way as some other studies. I will say that, at Case Western and at Ohio State, where they're doing BCI control of FES of the hand, they have reported an increase in hand function by using this BCI over the long term.
Evan, there's a lot of questions. Evan Chesanek says, your sensitivity metric for the middle and ring fingers reduced from the 3rd to the 4th year, giving way to the index and pinky. Have you or can you analyze whether this is related to the stimulation received during use of the robot hand?
Yeah, most of our experiments that we do are actually not closed loop experiments. It's still really focused on trying to characterize the psychophysical properties of stimulation. What I would say is that our most stimulated electrode probably generates a sensation on the index finger. And so I would have expected that maybe that representation would have expanded over time just because we really focus there, but we didn't see it. I think that it's potentially two things. One is that the array could be continuing to settle into cortex. And so we're just actually accessing different populations of neurons as that array settles, or that long-term stimulation has just made him more sensitive or aware of these sensations. And so we're able to, have him just describe this with a little bit more spatial accuracy.
Quick question from Matthias Franken. How much training do participants typically need to perform these tasks? And do you know whether adding the somatosensory input increases the learning rate if you were to include it from the very beginning?
Yeah, I think at a really high level, I almost say that there is no learning required to use these devices. And so for our participants, really from the very first time they use it, they can move the arm around in 3-dimensional space with, a 5-minute calibration. And so I do think we're picking up on these natural motor commands. And this has been replicated by other human BCI groups as well. You can do a very rapid calibration for these simple tasks. Now, certainly there is some learning that is happening. Even in our earliest studies, we saw that the firing rates that we were measuring had a stronger fit to our tuning models after long-term use. And so I think there are more subtle aspects of learning, but it's not that they are learning a completely new way of thinking. We're just refining our ability to measure that from only 200 neurons.
Yeah. So we're getting close. Well, we're beyond our scheduled time, but maybe just one last question, if that's all right. Evan Chesanek asks, have you tested for anything like a slip-driven grip force reflex? I'm wondering if something like a fast feedback loop could develop within motor cortex. So how quickly can people use this information to make corrections?
Yeah, honestly, we haven't explored that too much. So our system, it operates pretty quickly. We have an update rate of every 20 milliseconds, but there's a lot of smoothing in our neural decoding, and so it's a little bit slower than that. Part of the reason that we haven't is just because we feel that most of the natural slip responses are mediated more in the spinal cord or reflex loops rather than in motor cortex. And we want to focus on things that the participant needs to volitionally control and maybe offload some of that to either the robot to maintain that force. Doesn't mean it's not an interesting question. It's just not where we've prioritized our experiments yet.
Okay, great. Well, I think really fascinating and terrific work. Thank you so much for the talk. There are more questions, but I think we've bombarded you with enough questions for now. But I think someone's taking note of all the questions, so we'll forward the rest of them all onto you. So yeah, thanks very much again, Jennifer, and thanks to all our speakers today. We will be back tomorrow morning in Eastern time at 11 o'clock. So thanks to everyone for today, and we will see you tomorrow. Thanks very much.
Thank you.
Bye.
Bye.
Thank you all.